it works. I might not do this, Marco, but if we feel like it makes sense, I do have this video in my extra slides, and it actually works with the sound, which is cool. Yes, I was. Thank you. So which is good because the.
So good morning, everyone. Welcome to this plenary talk. I'm Marco Romoli. I'm the chair of Symposium 390 on a multi-point of view of the sun, advances in solar observations and in space weather understanding. The sun is our star. It's an astronomical object, of course, but it's also something more. It's the key to understand the stellar physics, and it supports life on Earth, and it determines this delicate equilibrium, which is the climate on Earth. So it's important to observe the sun continuously. There are still mysteries to solve in the sun. There is the solar cycle, the acceleration of the solar wind, the heating of the solar atmosphere that needs to be well understood. The sun has been observed continuously for many decades from space and from the ground. I just mentioned a few space missions, observatories like SOHO, Solar Dynamics Observatory, Stereo. And recently there is a new large telescope that is operating from Hawaii, DKIST, that is observing in detail the surface of the sun. And there are two new missions like Parker Solar Probe and Solar Orbiter. They are orbiting the sun, so giving a new point of view of the sun. Parker Solar Probe has a very has an eccentric orbit that will has a perihelion at less than 10 solar radii from the sun. Solar Orbiter also has an eccentric orbit that gets close to about 0.29 astronomical units, and starting from next year, it will be tilted in order to observe the poles. So these new missions, together with the ground-based telescope, will give us a new inputs to the understanding of the sun. In addition to that, there are two new missions, a Chinese mission, ASOS, and an Indian mission, Aditya L1, that will support these observations. So a lot of exciting science will come out from these observations. Today's talk is about these observations, their results, and the unveil of the sun's complexity, and also about the future on sun exploration. Today's speaker is a senior scientist of the High Altitude Observatory in Colorado, where she served as solar section head, deputy director, and interim director. Her research centers on the solar driver of the terrestrial environment. I met her at the beginning of the SOHO mission, and when she led the International Whole Sun Month campaign that brought new results on the sun. She was coordinating the observing and the modeling effort to characterize the sun and the heliosphere at solar minimum. She's a project scientist of NASA's Punch mission that will be launched in the next months. And during this GA, she will just complete her sequence of terms as vice president, president, and advisor for the IAU Division E on sun and heliosphere. So I'm pleased to introduce Dr. Sarah Gibson.
Thank you so much, Marco. Thank you to the organizers. It's my pleasure to be here. I was asked to talk about the future of Sun-Earth connection science, and I kind of went back and forth on the title, which is why I have a different title here, starting out with the concept of magnetism across time and space, because magnetism lies at the heart of everything I'm going to be talking about today. It's what controls space weather, space climate, from the sun to the Earth. Magnetism is the reason that a solar flare or a coronal mass ejection at the sun impacts us here on the Earth. It's the reason for the beautiful complexity that I'm going to be showing you, because with every observation, all these telescopes that Marco talked about, we see something new that inspires and teases us with a new magnetic mystery. And what do I mean by beautiful complexity? Well, for example, this picture, but there are many more. So, I get ahead of myself because I actually landed on a different title. Because when I thought about these questions and really what I wanted to say today, I kept coming back to the 1888 Satirica novella, Flatland, by Edwin Abbott. Because what I want to talk about today is how do we take full advantage of the proximity that we have to the sun to really understand its full three-dimensional and global complexity. And now Flatland is a story about a square. It's about a world where everything is two-dimensional. And this square has a sequence of dreams. In the first dream, he goes to a world where everything is one-dimensional. And he tries to explain the concept of two dimensions to these one-dimensional creatures and is unsuccessful and is basically has to run for his life to survive. The next night, he has a second dream. And in this one, he is visited by a sphere. And the sphere explains to him the concept of three dimensions by having him fly up and down past her and see her cross-section change. And he's inspired and he understands and he goes back, wakes up, and he tries to explain to the world, the two-dimensional world of Flatland. And of course, they throw him into jail. But anyway, so this was my inspiration. But I'm going to be talking about Beyond Flatland, a star of many dimensions, our sun. How do we get past our ecliptic bias and really see it for the full three-dimensional object that it is? And I'll start by going back and talk a little bit about a brief history of our evolving appreciation of the sun, introducing solar magnetic mysteries that have run through the observations from the beginning. Then I will focus in a couple areas. The first one is to look at the ubiquitous magnetic flux rope, which is a magnetic structure which is three-dimensional and twisted, and which lies at the heart of the concepts of magnetic energy storage and release. It shows up in the sun, and it shows up throughout the universe. And I'll talk a little bit about some upcoming missions and projects. And then in the last part of the talk, I will talk about the ultimate travel beyond Flatland to seek a polar perspective, to get out of the ecliptic and go to the high helio latitudes, why we need to do this scientifically. And I'll talk a little bit about upcoming missions and projects again. Okay, so this is the ultimate kindergarten picture of the Flatland sun with its rays pointing out. Perfect, unblemished, round. It didn't take long to get beyond that. In the 4th century BC, I believe, there were already records of sunspots taken by Chinese astronomers. So the sun is not a perfect, unblemished sphere. And then, of course, in the 16th century, when the telescope was invented, we could confirm that and then see that the sunspots happened all the time, at least most of the time at that time, and also that the sun rotated. And this is an interesting point. Galileo was not the first to observe sunspots. Scheiner actually was the one who first observed sunspots through a telescope. But Galileo got it right as to why the sunspot moved across the disk. There were different theories and what they were. Some theories, for example, were that there were planets very close to the sun that were moving, orbiting the sun, and that's what we were seeing crossing the disk. Galileo got it right that, in fact, the sunspot was on the surface of the sun, and its motion was indicating the rotation of the sun itself. Moving forward in time, we see that the cycles, that the sunspots happen all the time and that they're cyclic, that they wax and wane with a period of approximately 11 years, going from a maximum when there are many sunspots to a minimum when there are not as many. This particular picture shows Annie Maunder at her telescope, and Annie and Walter Maunder together came up with the first solar butterfly diagram, showing by painstakingly recording the location of sunspot emergence versus time, that they start at high latitudes and then, as time goes on, emerge at progressively lower and lower latitude, letting the the butterfly spread its wings. This particular picture is just around the corner from my office at IAU in Boulder. And it has a letter that accompanies it that's quite wonderful. It's by Annie Monder, and she describes how, as she puts it, a week of evenings, she and Walter took turns drawing the little sunspot on the diagram and making note and calling out its latitude versus time to the other. And so this picture and that letter are recorded at IAU. Now, as time goes on, in 1900, George Ellery Hale observed that sunspots had very strong magnetic fields, 1,000 times stronger than anything observed or in a lab on the Earth. And moreover, looking at that butterfly diagram and putting together the records over time, we see on the top the butterfly diagram where you're looking at latitude versus time, and on the bottom, the sunspot number cycle where we're looking at the number of sunspots versus time, their amplitude. And you can see this quasi-periodic behavior. It's about 11 years, but it's not exactly 11 years. As time continued to go on, we saw that we used helioseismology, which, like seismology in the Earth, can penetrate the depths of the sun by looking at motions at the surface. And from this, we learned the flows inside the sun. We started to go truly into the third dimension of the depth of the sun. The upper plot on the right is showing you differential rotation. And actually, we already knew from sunspots, just by observing the patterns of sunspots moving across as the sun's rotated, that the sun was not rotating as a solid body, but it was going faster at the equator than at the poles. And you can see in this upper right picture, red is faster and blue is slower. And what helioseismology did was show us that this pattern continues as we go deeper into the sun's interior. As you get deep enough, though, the color turns to yellow all around and you have a solid body rotation below the solar convection zone. On the bottom right, we have another kind of global flow, meridional circulation, which is a flow from the equator to the poles at the surface. And it's possible that there's a return flow, like a conveyor belt going from the equator to the poles and then returning, going from the poles back to the equator at lower depths. But at this point, we don't have enough observations to truly confirm that, but that is possible. And it would help us explain some magnetic mysteries, because one of the most prominent magnetic mysteries that this raises is, how does the sun create and sustain this cycling magnetic field? And this is really the question of the solar dynamo. And Gene Parker, who's shown here, had the insight that a differentially rotating fluid body like the sun could take a magnetic field. If it starts out as a dipolar magnetic field, the differential rotation would shear it in such a way that that poloidal field would transfer to toroidal field, the so-called omega effect. But then you need a way to have that toroidal field go back to the poloidal field, which is tricky. But again, Parker had the insight that Coriolis effects, force acting on rising turbulent fluid, could indeed transfer toroidal field, to poloidal field. But the devil is in the details, because whether that happened in a distributed way throughout the convection zone, which in fact was what Parker originally was modeling, or whether it happens through a sequence of global flux transport processes, is something that is still something we still struggle to understand today. And for example, this is one model of how it might occur in a global way. If you start out with a dipolar type magnetic field, like the picture on the left, and so you have a poloidal, or essentially at the equator, north-south type magnetic field, and then you rotate it, you end up with a toroidal component, and then the buoyancy operating on this creates a local poloidal field at the surface of the sun. This is actually then the emerging sunspot, or active region, which is what we call it when we observed it in the short wavelengths. And then, because of that conveyor belt of meridional circulation. It is transported to the poles through surface flux transport, and it creates a global poloidal field of the opposite direction from your initial one. So this is one nice way of getting this kind of evolution happening. And it's a way of, for example, setting the 11-year solar cycle clock, which is basically then controlled by that speed of that meridional circulation transport. But there are other ways to create, you can create a oscillating dynamo without ever needing sunspots, because it can happen in a local way throughout the convection zone. If you have helical turbulence, there is a transfer of the poloidal north-south type magnetic field locally into the toroidal and vice versa. And simulations which essentially just have those sort of turbulent processes happen can then, interestingly, create global structures like the toroidal magnetic wreaths that arise from these interactions locally in the dispersed flows. So you can come up with something which is related to the sunspot toroidal pattern, for example. So the question is, which of these processes are the dominant ones? And there it comes down to the magnetic mystery. Well, actually, it's not really a magnetic mystery, but the mystery of what kind of star the sun is. And I mean that dynamically now, because what we need to understand is the degree to which rotation, stellar rotation, affects the convection in a star. And if you have a non-rotating, fully convective star, like on the left, then you are in the regime of high stellar Rossby number. And if you have a very, very fast rotator and or weak convection, as in the far right, then you're in the regime of the low stellar Rossby number. And we know the sun is in the middle, because we know that we observe convection, for example, at the surface, so it's not on the far right. We also know that it's rotating, so it's not on the far left. So it's somewhere in the middle. And it's important to figure out where in the middle it is. Is it right on that boundary, that Rossby number of 1? Or is it maybe less than that? Because if it is less than that Rossby number 1, the rotationally, so it's more towards the rotationally dominated flow, then turbulent dynamo processes become more efficient because that helical motions are more, it's more tightly, it's more efficient, basically. Okay, so let me go to another magnetic mystery which Marco mentioned, which is the fact that as in the 19th century, spectroscopy started looking at the atmosphere of the sun, something peculiar was seen. It was peaking in a sort of a green line, and at first there was they actually gave it a new name, an element of coronium, to explain this structure, this observation. But by the 1930s, it became clear that actually what we were looking at was an iron line, but one that was so ionized that half of its electrons had been ionized. And that implied that the corona was 1,000,000 degrees. Now, the sun is about 20 million degrees at the center, and as you get out to the surface, it reaches about 5,600, right at the surface or photosphere. But then, very quickly, in a very small layer, it jumps up to 1,000,000 degrees. So how does that happen? Why does that happen? And this is something, as we then started to observe and actually send, for instance, Skylab up above the Earth's atmosphere, we were able to look at short wavelengths. And when short wavelengths of soft X-ray, extreme ultraviolet, we really see the structure of this solar corona. And you see these dark regions, for example, in the middle image. These are what are called coronal holes. And coronal holes are interesting, and I'll come back to them, because these are regions where it's believed that the magnetic field is open to the solar wind. So this is where the solar wind gets out into the heliosphere. So that is, of course, the solar magnetic mystery of how is the corona heated to 1,000,000 degrees. And it was, again, Gene Parker's insight that the very small current sheets would form between magnetic structures, which are very three-dimensional, so not smooth, and you get these discontinuities, and you get these very, very small flare releases of energy. They're called nanoflares, and that this is a way of transferring the magnetic energy into thermal energy. Because I'll give you a short answer to pretty much all of these magnetic mysteries, the answer is the magnetic field is how it's happening. How is the coronal heated? It's magnetic energy transferring to heat. But how? And so nanoflares is one possible way, but there's another possibility. Waves in the corona are observed all the time. These are what are called spiculas, and they're waving around like blades of grass in the lower solar atmosphere. And waves are a way where, again, you can transfer energy from the magnetic field into the corona. But which is the dominant process? This remains something which drives us to continue to get observations at higher and higher spatial and temporal resolution. And it's these observations at high temporal resolution which also introduces and exposes solar dynamics, which go along with this magnetic cycle. And what you're looking at in the middle is the eruption, if you can see, let's see if I can point to it. This dark structure is what we call a solar prominence, which is relatively cool, maybe 10,000 degrees Kelvin, plasma, dense plasma, that is suspended in the very hot, sparse coronal atmosphere. And of course, what it's keeping it up is the magnetic field. And also, it is the dynamics of its eruption as the kind of the core or the heart of a coronal mass ejection, or CME, that is controlled by magnetic instabilities and various reconnective processes that I'll talk a little bit more about in a moment. So that is then a whole suite of new magnetic mysteries. What is the three-dimensional structure of the magnetic eruption precursors? How does the energy build up? And then what triggers its release in a coronal mass ejection? And how do these CMEs, coronal mass ejections, evolve as they move from the sun to the Earth? And of course, that's where space weather comes in. Because when you have a storm at the sun, both the flare itself and the coronal mass ejection has an impact at the Earth. And space weather is something which has been around forever. There was always a potential for beauty from space weather. Up until 150, 200 years ago, that's what we got. We got beautiful auroral light shows, and we still get those. We had one just a few months ago that a lot of us were lucky enough to see. But now we are a technological society. And now there is actually a potential for danger, for risk to our technological assets, both on the ground, with power grids failing when you set up geomagnetically induced currents, ground currents, to satellites failing when you have energetic particles from the sun essentially causing system failure. And then, of course, there's risk to life, not really to life on Earth, because we've got two wonderful things acting on our behalf. We have an atmosphere full of water, and we have a magnetic field which blocks the worst of this space weather. But when you get high enough up, if you're an airplane pilot, or most particularly if you are an astronaut flying, for instance, from the Earth to Mars, you are exposed. And so understanding space weather and its origins in the sun and its evolution through the heliosphere and interaction with an Earth's planetary magnetosphere and atmosphere is absolutely crucial as we continue in our spacefaring ways. Okay, for my last sort of magnetic mystery, I'm going to go back to, again, Gene Parker, who had the insight that, and it's really kind of a corollary to the coronal heating problem, which is how do we get a solar wind, a fast solar wind? And in fact, what Parker argued was that it was inevitable when you have a hot corona that you will end up with a supersonic solution of mass plasma streaming outward from the sun. This was a theoretical paper, and it was kind of largely ignored for a while until Mariner spacecraft flew and did an in situ measurement, put down a bucket and measured the plasma there and saw, yes, indeed, there was a solar wind and it was streaming outward. And so it's a fitting tribute to Gene Parker that the Parker Solar Probe mission was named after, in fact, it was the first time it was named after a living astronomer, a NASA mission. Parker Solar Probe is getting in closer to the sun than any mission before that, within 10 solar radii. And this is an example of its orbit. Now, of course, there's two ways we observe the sun. We observe it through remote sensing, and because we're so close, we have the proximity, we can measure things in situ. And Parker Solar Probe was launched, Parker himself was there at the launch, I believe it was in 2018, and was very involved in some of the early discussions. Sadly, he passed away in 2022. And one of the things that Parker is sampling is the riotous torrent of the outer corona, which is the true kind of boundary of the solar wind. It's the place where the magnetic field of the sun itself and the solar corona becomes, is duking it out for dominance with the kinetic energy of the solar wind. And even from our remote sensing observations, this is a very high resolution stereo coronagraph, deep field campaign, we could see that it's not smooth. I remember learning about what we call the Alfvén point when I was in school, which is when you just sort of say, okay, what's the speed of the solar wind? What's the strength of the magnetic field? Where does the Alfvén speed become lower than the outflow speed? It's a point in space. And then I remember people started to talk about it as an Alfvén surface because they had these nice MHD global models, and you could sort of see that, oh, it's kind of this location in space, but it's more two-dimensional. Well, these observations make it very clear that it's three-dimensional. It's frothy, the Alfvén zone. And it's the magnetic field, the density, it's all structured. And that's what Parker is flying through and measuring in situ. And so we have a whole new set of magnetic mysteries that we've got from this. Where and how does the solar wind dominate over the magnetic field? Why, this is something I'll come back to, is the polar magnetic field that we measure at the sun from remote sensing inconsistent with what is measured by spacecraft that have flown over the poles, for example, the Ulysses spacecraft? And what are the magnetic switchbacks that are observed by Parker Solar Probe? And these are structures where you see a sudden reversal in the direction of the magnetic field on in structures that are flying past Parker Solar Probe. And there's a variety of theories of magnetic switchbacks. Essentially, they're a kink, and there's Alfvén waves moving outwards. And one prominent theory is that they're due to reconnection, perhaps low down in the solar corona. What is that magnetic structure? And I've put this in as transition to my next part of my talk, because one of the early theories had to do with the creation of a magnetic flux rope. And this is a magnetic structure which keeps coming up on every spatial and temporal scale that you can imagine from sun to earth. And so let's go to that, the magnetic flux rope. Okay, well, what do I mean by a magnetic flux rope? Essentially, it's anything where you have magnetic flux wrapping around a central axis or axes, which gives you topologically distinct magnetic subsystems. And on this particular plot I'm showing you on the left, a classic, we call it a slinky, but it can actually be not very tightly wound. You can have a single wind. All you need is one wind topologically to make this a flux rope. Single axis, or you could have something more complicated like a spheromac, where you have two axes of rotation. And the question is, what do they look like? How would we actually observe them? Well, every image shown here is something that at one time or another has been described by a magnetic flux rope. Here's the models that go with them. And I'm going to touch on some of these and basically give you a little bit of a life story of a magnetic flux rope, how it appears from its origins all the way through the solar wind. So first of all, where do they come from? Well, we can go back to this picture of the solar dynamo. Again, that transfer of toroidal magnetic field to poloidal field through buoyancy and twist. Flux ropes are a magnetic structure that forms when you have that kind of large-scale transport of twist from the solar interior. But does this magnetic flux rope, if it's formed in the interior, and simulations have demonstrated it can be, does it just sort of smoothly emerge out into the solar atmosphere? Probably not. Simulation, because you've got this tremendous, you go from a very, very dense solar interior to suddenly a much sparser solar atmosphere. And simulations argue, or have shown that what's probably going to happen is if you have dips in the magnetic field, it'll get stuck as it tries to come out through the surface. But the interesting thing is that they come back. And so this is an example of a simulation in which a magnetic flux rope from below the surface is emerged through that very strong change of density, that surface of the sun, into the corona. And again, indeed, it is stuck, but through magnetic reconnection, the twist that has come through is kind of shredded and brought back together. There's an inverse cascade of magnetic helicity it goes from a large-scale type magnetic structure to something that shreds to something that goes back to its large-scale magnetic flux rope type formation. And in this sense, this kind of gets at why magnetic flux ropes are so ubiquitous, because they represent a minimum energy state for a given amount of twist or magnetic helicity. And I talked at the very beginning of the talk about solar prominences. These are those cool, dense material it's basically 10 times higher density, 10 times more or less, or 100 times lower temperature. Let me get that right. And it's cool and dense, and it's suspended in the hot, sparse corona. So this with simulations, we can demonstrate this is expected when you have something like a magnetic flux rope, because the magnetic field lines, the dips in the flux rope, act as a cradle where the prominence can form thermodynamically. And these magnetic prominences, I'm showing what they look like on the disk on the left, top left. They're dark in H alpha up against the solar disk. Can form both in small kind of like regions associated with active regions or very large scale structures. This one is a large scale, what's called a polar crown prominence. It's like a crown around the sun at high latitudes. And it's a large scale magnetic structure with a prominence, also known as filament, if seen on the disk, that extends right way across the sun. And when it's seen at the limb and the corona, you have the prominence as a bright structure now, or dark in absorption, and it's surrounded by this elliptical structure called a coronal cavity, which is like a magnetic tunnel that surrounds the prominence. And we can go back to one of those magnetic mysteries, which is what is the three-dimensional magnetic structure of the precursors to solar eruption? Because when you have a flux rope, not only do you have dips where the mass can collect, but you have, it's only a very small part of the volume, right? The prominence is just like little tiny pieces of that large three-dimensional magnetic structure. The volume itself is represented by this coronal cavity, which is seen in projection at the limb or the edge of the sun. So one possible 3D magnetic structure of these things is a magnetic flux rope. And they do erupt. This is an example of one of these coronal cavities over the course of a day or two, in this case, narrowing, rising, slowly, showing enhanced substructure, and ultimately erupting out as a coronal mass ejection. And this brings us back to another solar magnetic mystery. How does magnetic energy build up in the corona, and what triggers its release and eruption? In theory, in simulations, you can have a situation where you have the magnetic twist emerging from below and slowly coalescing over time into a large-scale twisted magnetic flux rope. And when it reaches, and so it finds a temporary equilibrium. These cavities can exist, and prominence can exist for days and days and days. Depends on if it's a large-scale polar crown prominence or if it's an active region as to how long it might live. But eventually, it gets to a point where you have all this magnetic energy and helicity that just can't stay put. It has to erupt. And in this particular simulation on the right, you can see there's a temporary equilibrium happening now. And then through a process which is enhanced by reconnection, magnetic field lines are getting kind of reconnecting below the structure, so it rises a little bit higher, like in the observation on the left. And eventually, it gets to a point where it is unstable. It's unstable to the torus instability, which is essentially, it's a process where you have the magnetic hoop force wanting to go out, and then you have a strapping force by the overlying magnetic field that's keeping it in. If it goes high enough up in the atmosphere, it will erupt. Okay, so the magnetic fields are pretty central to this, right? You want to know Is it high enough to have this eruption? Is it going to erupt? If you want to predict space weather, you want to know how likely this magnetic structure that you see is going to erupt, and how soon. So we need to measure the magnetic fields. Well, there's only one place at the moment that we are measuring the magnetic fields, and that is in the solar wind, in situ, because magnetic clouds is what you call an in situ observation or measurement of a magnetic structure that's passing your spacecraft. And you see a rotation, which fits quite nicely with the model of a flux rope passing your observation. And that's what these images on the right are showing, is your three-dimensional rotation. And that can be measured in situ. Now, of course, that's tremendously powerful because it's a true measurement. But the dimensionality is basically one-dimensional, right? Because you're just seeing something pass a single point in the 3D heliosphere. Where do we want to measure the magnetic fields in a flux rope? And the answer is everywhere. But especially the solar corona, because it's the sun's atmosphere where the magnetic fields come up and the energy builds up and is stored before it is released. And this represents a model, these images, that is an alternative to that flux rope reaching a torus instability and erupting. This is what's called the magnetic breakout. And the concept, all of these models are really talking about a fight between the flux rope, which wants to go up, and the overlying field, which wants to keep it down. And that could happen through an torus instability where it goes up high enough that the flux rope wins and goes, or the magnetic breakout essentially is a reconnection above the flux rope, which takes the lid off, and the thing can erupt and escape. And this comes down to one of the kind of controversies in our field is, was the flux rope really there all along as a metastable kind of place where you're building up magnetic energy? Or was it actually created by the reconnections that are fundamental to this breakout process? And my personal opinion is it depends where you look. And if you're looking in an active region, you may well have something like the breakout happening. But when you're looking at a structure like those coronal cavities, then you already have a magnetic flux rope. But it makes a difference because how are you going to know when it erupts unless you know which process is actually occurring? So that is the magnetic mystery revisited. What is triggering this release? Okay, how can we measure the magnetic field of corona? Well, spectropolarimetry as well as coronal seismology, especially in the visible and the IR, but also in the UV and even the EUV, may be used to determine the coronal magnetic field topology and strength, both of which are important. Observations today, the COMP telescope on Mauna Loa observes linear polarization in visible and infrared light and is able to look at the topology. For example, the breakout topology of having a place where you can have reconnection above structure, a magnetic X point, is something which has a signature in these observations. The strength, which we want because the magnetic energy goes as magnetic field strength, one way you can get information is by looking at seismology, coronal seismology. So what you're looking at here is alphanic waves in the corona, and by measuring them, you can basically back out the alphane speed, and if you know the density, you can get out a plane of sky magnetic field. But we really, really want, because a lot of the twist and the strength is contained in shear along neutral lines, which are often along your line of sight, is to get magnetic field measurements, Zeeman measurements, along the line of sight. And the DKIST cryo-NIRSP instrument on the DKIST telescope is the first place we really can get that. And there's observations just now being obtained and analyzed with this in mind. But to be honest, DKIST is going to be fabulous for observing and getting this information in a small field of view because it's a telescope that's ultra high resolution but has a very small field of view, so maybe an active region size or smaller. We need to get away from flatland, and we need to look at the global sun. So we need measurements of the whole sun synoptically all the time. And that's why the Mauna Loa Solar Observatory is moving in the direction of the Coronal Solar Magnetism Observatory, or COSMO. And essentially, we've done the forward modeling to say, how big of a telescope do we need to make to be able to observe globally and sensitive enough to look at the magnetic field strengths, the line of sight magnetic field in CMEs, so that we can actually see them erupting? And the answer to that is about 140, 150 centimeters. So that is a telescope which is currently in the essentially pre-proposal stage. We're doing a site survey and an instrument design. We've been funded for that. Okay, we leave the corona. The flux orb leaves the corona and it moves out through the solar wind. And this particular movie is patching together a sequence of solar and heliospheric observations, but it's been kind of stretched out so you can see the structure. So on the right, with the blue image, you're looking at the lower corona in extreme ultraviolet. And then the next image, moving out to the left, the solar corona, is a coronagraph image, and that's simulating a solar eclipse, blocking out the surface of the sun and getting a coronal image. And then, let me see if I can get it to run again. Then we have what are called heliospheric imagers, which off-point from the sun, and you can continue to see the solar wind and the structure. And you can see these things moving through the solar wind, and in a second, I think you're going to see, here we go, on the far left, you have near-Earth heliospheric imager, and when it hits the Earth on the bottom right, you'll see the density swing to the right because you've got a large-scale dense structure passing the Earth. But our field of view is quite limited. We have a lot of gaps in this image. We don't quite know what's happening between the corona and the heliosphere. There are structures that look very radial and striated that get very clumpy in the heliospheric imagers, and we don't know if that's different instruments that are causing it, or possibly it's because fundamentally turbulence is starting to play more role in the solar wind as you cross over into the inner heliosphere. So there's gaps. There's also gaps at the poles. We don't see the poles. So the PUNCH mission is going to be flying next year, and it actually gets that field of view. So on the right-hand side, you can see the full field of view of PUNCH. It's observing. It's basically as though you were, because when you start to observe away from the sun, you can no longer talk about a plane of the sky. We're definitely moving beyond flatland, and you're looking at something which is very spherical. And so you start measuring not in terms of solar radii, but in terms of elongation angle. So we're talking about 90 degrees of elongation angle. So you're going from the horizon to the zenith, and the sun's in the middle. So it's a huge field of view. We're going to be able to observe these coronal mass ejections and other solar wind structures move out from the sun into the solar wind and how they evolve. Because they start out in a certain way, but they bump into other coronal mass ejections and other solar wind structures, and they change as they go. And again, if you want to understand what hits us here on Earth, you need to see what happens between the sun and the Earth. So this is the mission. It's a small explorer. And I just wanted to highlight here that it also gives you information in 3 dimensions, even though when you observe the corona and heliosphere in white light, you're observing an optically thin phenomena. So you're piling up all the density along your line of sight, which loses information along that dimension, the line of sight. But because PUNCH is a polarizer, it actually observes both polarized brightness and total brightness. It's able to back out the location of structures, superparticles or CMEs, along the line of sight. And that brings me to the last part of my talk, which is really getting the 3D away from flatland view. How do we move away, in particular, from the view which is really dominated by the fact that we are very close to the solar ecliptic, the Sun-Earth line. Now, we've had 2 wonderful missions that have helped us with this. The first is the stereo, where there was a spacecraft ahead and behind the Earth, lagging and leading, and so we were able to get multiple lines of sight from essentially near the ecliptic, but to see structures on the far side, for example. And then Solar Orbiter, which is also like Solar Probe, Marco mentioned, doing an extremely elliptical orbit, getting close to the sun, but also beginning to move out of the ecliptic, and it will actually get up to 30 degrees. So it will start to get views that we have never had before. And the reason we need that is right now, the way we really understand what's going on at high latitudes in the sun, inside and out, is by taking a boundary condition, a very important boundary condition, at the solar photosphere. We can measure the magnetic fields quite well there, but we're looking at a sphere, and we are measuring something in 2 dimensions. So, for this reason, we have all sorts of effects, projection, foreshortening. When the magnetic field is mostly radial at the poles, that means that you don't really see much of it when you're observing line of sight field. There's a lot of problems. And so we have to basically come up with empirical models of how the magnetic field changes as it gets to high latitudes. And for this reason, we don't have agreement. This on the bottom right is showing you two magnetograms. And so what you're seeing is it's the spherical field that you see in the big circle on the left, but it's been unwrapped into the latitude and longitude. And the information at the poles from these two instruments, same color scale, you can see that the one on the left is much stronger, is predicting a much stronger magnetic field at the poles. And that's because there's so much uncertainty intrinsic to the fact that we are observing the sun from the ecliptic. So for that reason, we really don't know the polar magnetic field strength or its distribution for that matter. And this gives you a sense of what we can learn, for example, by the fact that the Earth is moving by 7 degrees up and down. And this is really how people are currently coming up with corrections and these models for how the field changes as you go towards the poles, is by looking at the annual change of 7 degrees. But you can see you're really not getting much more view. This is the same simulation, just showing you what you would see from the ecliptic at 7.25, and even from solar orbiter, which is really going to be, it's going to be a pathfinder, it's going to show us something important, but 30 degrees is not enough to really look down on the poles. And on the right is if you could truly look from the top. And that brings us back to one of our solar magnetic mysteries. And I mentioned that the polar magnetic field measured to the surface and is inconsistent with what has been measured in the solar wind. And we did have a mission, the Ulysses mission, ESA's Ulysses mission, flew to the high latitudes and went over the North and the South Pole more than once. And so we have a sense of what the magnetic field is in the solar wind at 4 AU above the poles. But all these different models and these different observatories, even with that uncertainty, we're still more than a factor of 2 off compared to the solar wind measurement of magnetic field. And so this kind of illustrates, there's different ways that we had a talk, I think yesterday in Symposium 390 about this. There's different ways you might fix this problem, but this illustrates one of them, which is what if we had a top knot of magnetic field, strong magnetic field, really concentrated in a place where we really couldn't see it? Because for most of the solar cycle, you have something which is kind of dipolar, especially at solar minimum, it's very dipolar. So you have magnetic field coronal holes associated with them at the poles. And these are 3 different models where different polar models, all of them consistent with what could be observed from the Earth, but all of them very different in their implications for the heliosphere, with a strong magnetic field and a structured magnetic field. So we need a polar field to really tell. We need unobstructed, unprojected measurements of both magnetic fields and flows, because this photospheric field is not just the lower boundary on the heliosphere, it's the upper boundary on the dynamo. And I've already mentioned the flows that we found from helioseismology, these axisymmetric mean flows of differential rotation and meridional circulation. There's a big question mark at the poles. We know that the equator is rotating faster than high latitudes, but those high latitudes only go so far. Right at the poles, we don't know. It is possible, simulations have shown that it is possible, that the flow may shift back to prograde at the poles, so that it goes faster here, slows down at mid-latitudes, and then speeds up again at the poles. And I'll show you there's a significance of that. The meridional circulation. We know we go from the equator toward the poles, but this is a very weak measurement. The amplitude of these flows are small. So we don't really know, and again, we get all the effects of the foreshortening at the poles. We don't really know if there is a high latitude countercell. Again, this can happen in the simulations, and it has a huge impact. It's been proposed that this is one of the reasons why we sometimes have 11-year solar cycles and sometimes have longer cycles or shorter cycles, is the presence or not of such a countercell. And then for that matter, we don't really know what's happening. We know that sunspots appear in the sunspot butterfly from sort of mid to high latitudes down to equatorial. We don't know if there's smaller scale flux emergence or sinks at the poles. And this has an important impact on the flux budget of the sun. And finally, convection. In addition to those 2 flows, those axisymmetric flows of differential rotation and meridional circulation, there is 3-dimensional turbulence going on throughout the sun, and there is convection in the upper third of the sun. And if we could view the solar convection from the top instead of the side, there's a fundamental difference. One of the questions is, are these convective cells spherical, or are they more columnar? This impacts which part of the Rossby regime we are, what kind of dynamic star the sun is. And if you look at something that's columnar from the edge, it just kind of looks sheet-like. But when you look down on it, it looks circular, vortical. And so if we could get that view, we would have an important piece of the puzzle. And so this is kind of a summary of all that. So these are 3 global convective models going from bottom to top, the convectively dominated to more rotationally dominated, and the 3 types of flows. As we go to the more columnar flow, the size of those structures will get smaller, and it turns out you can analytically show the relationship between that size of those vortical flows and the Rossby number. And in fact, so we call them spinning gyres, that we can directly relate that size to the strength of the global deep convection. In differential rotation, the question is, does this pulse, do they speed up or do they slow down, keep slowing down? And if in fact they speed up, so we have a prograde, that indicates that the sun is right at that boundary of rotationally and convectively dominated regimes, Rossby number 1. On the other hand, if we see meridional circulation with equatorward, so a countercell at the poles, that indicates rotationally dominated flows. And again, if it's more rotationally dominated, the turbulent dynamo processes become more efficient. But it's not just the dynamo, because the photospheric magnetic field is the lower boundary on the corona and heliosphere. We have both open magnetic fields to the solar wind and closed magnetic fields, which are the ones that store the energy and build up things like flux ropes. And here's an example of that polar crown seen from above. Right now, we've always seen just a front side view. And so if we could observe from above, we could see the processes that create these large-scale structures. And it's particularly interesting because these larger scale polar crowns, as opposed to the sunspot-related flux ropes, happen on longer time scales. It's easier to actually kind of understand the physical processes. And the view we need for that is from above. But the open magnetic fields, the coronal holes moving out into the heliosphere, if we can observe from above, we could look at the magnetic field at the sun, the magnetic field in the heliosphere, and really put those pieces together. And then as we move out, this on the left is a model, a simulation from the polar view, because we don't have the observations yet. If you could look down on the sun, you could see all those coronal mass ejections and other structures moving through the heliosphere, not just the ones that happen to be kind of pointing at us or on the edge, but all of them, and how they're going to intersect all the planets, not just Earth, also Mars, which is quite important. You could look at the structure and evolution and global interactions. Remember, I mentioned CMEs run into other structures from that crucial view down the rotation axis of the sun, and see that as the CMEs move out. Okay, so when should we go? And the answer is no, now, not no. Now, because, I mean, this is compelling science. This is a really crucial missing piece of the puzzle, is the polar view. And we've got Parker Solar Probe, we've got solar orbiters, so we should go as soon as we can. And we know it's possible because I mentioned the Ulysses, which used a gravity assist from Jupiter. So that's the hard part, how do you get out of the ecliptic? We know it's possible. The Solaris mission was a mid-X phase A concept study a couple of years ago, which demonstrated the readiness to do this kind of a mission with remote sensing observations. And part of this concept study was really to ask the question of how high do you have to go to really actually answer these questions? And the answer was essentially above about 65 degrees heliolatitude. The point being that you have to be able to see the sun, the unprojected sun, you have to be able to see it so that when you're looking down on it, you're seeing get about 60 degrees of solar angle that is unprojected. That's true also from the ecliptic, looking at the sun front on. And to get there, you have to go above 60 degrees to get that view essentially continuously. And what this movie is showing is how important it is to get high enough for long enough that you can see, in this case, as you can see, one of the poles for at least 3 months, because when you do the analysis of the timescales of the flows, of how long you need to beat down the signal, the noise on the signal, you need about 3 months of observations. So it's possible and it's been figured out. And what are we going to find at the sun's poles? Well, I've been talking about what you might call the known unknowns, right? We know there's some crucial questions about solar magnetism and about the dynamo and about solar eruptions that need that polar view. But there's also the unknown unknowns. And if there's anything we learn from going to the poles of planets, Jupiter and Saturn, is the surprises. You know, Jupiter has these structures, these vortical structures that are asymmetric in size and number between North and South Pole. Saturn has this remarkable hexagonal shape. And so it's the nature of spinning spherical fluid bodies to reveal a lot of their internal dynamics at the poles. And so there are mysteries that are definitely going to be revealed when we get this view finally. Okay, so now I'm ready for my conclusions. And this is the running theme. We've been observing since at least the 4th century BC. And every time we observe, we get a new question. And this will not stop as we keep going. Magnetic flux ropes are really a fundamental building block. They show up all over the cosmos for energy generation, storage, and release. But their appearance, you really have to know, you're talking about a magnetic field structure, but what we observe is the plasma associated with that field. So depending on where the plasma is collected, what the temperature is, there's things that we have to basically combine to get that 3D magnetic structure. Punch and the proposed Cosmo are examples of new missions that are going to shed new light on how those magnetic ropes evolve from the corona to the solar wind. And then, of course, the question is, what are the dominant mechanisms of the sun's dynamo? Is it predominantly this sort of large-scale flow structure, or is it more localized? We need the polar vantage to measure the flows in fields and pinpoint that dynamic regime. And Solaris is an example of a mission designed to go high enough and long enough to solve this, as well as other outstanding magnetic mysteries. But ultimately, we're going to get new science because of new vantages, going somewhere we haven't gone before, but also because of global, continuous coverage of the sun's magnetic fields and flows, this full 4-pi coverage of the magnetic field and flow of the sun throughout the heliosphere. So thank you very much.
Thank you very much, Sarah, for this very interesting presentation showing how magnetic field rotation interact in this three-dimensional view of the sun. So any questions?
Microphone.
Thank you for that very inspiring morning talk. Yeah, it's gorgeous. So my question is, when would you want to go to observe the poles in the solar cycle, and what would be the difference at different times in the solar cycle of what you would perceive?
That is a great question. Any time in the solar cycle has something to tell you, first of all. If you're looking at solar minimum, your polar coronal holes are the best formed, and so you've got a kind of a simple magnetic structure that you can observe. But throughout the solar cycle, because coronal mass ejections tend to get deflected down to the ecliptic, as you get to solar maximum, you'll get more and more of these eruptions, so you'll have more of those to observe, and those will essentially get deflected toward the ecliptic, and so you'll be able to see them moving out. In terms of the solar dynamo, what you really want to do is to get a view on the flux transport at the poles. You want to be able to see this process, is there magnetic flux from lower latitudes getting pulled up? How high? Where do they actually subduct? And so you need a few months of that. For most of the solar cycle, you get a really important constraint on that. If you happen to observe right at solar maximum when the magnetic fields are reversing, you'd have quite a unique picture on that because you would be seeing the solar reversal happen from above. So any time is good. Yeah, I mean, yeah, any time is good, is what it comes down to. What you really want to do, though, is observe. You need to have to kind of answer these questions that I raised. You need about 3 months, ideally for both poles. But you really want to observe it over the course of 11 years to see how it changes. So an extended mission going on as to observe both poles is really important for that.
Yeah, great talk, Sarah. That Solaris mission, the Solaris mission that you mentioned as a study, how do we make that happen? Are there plans to propose that in the future?
That is a disingenuous question, Don, who's the PI of Solaris. First of all, you go to Don's talk this afternoon, and he will tell you. And so, yes, there are plans to repropose that because it made it to the cosmic concept study phase, but it remains an important thing.
Hi, Sarah. Dibyendu here. That was a fantastic talk. One of the unique perspectives that a polar satellite could do in conjunction with another spacecraft, somewhere in the ecliptic or somewhere separated in longitude, would be heliosseismic stereoscopy. What that could allow is imaging of the deep flows. For example, you said the maiden circulation, where does it turn over? We don't have much constraints on that. But this would require 2 spacecrafts. Is there any thinking along those lines that you could comment upon?
Yes, absolutely. Solaris is a way of getting to the poles right away and well, as soon as possible and kind of answering these questions. But ultimately, we have to build a constellation where we have more than one. And because you can start to do a couple of things, you can start to observe north and south poles simultaneously. And as you say, if you have multiple views, and this could be, for example, a polar view as well as an ecliptic view, you might be able to do deeper global helioseismology. So there's mission plans that have been proposed to the decadal survey. It's something that's being evaluated right now. The Firefly or the 4-pi configuration is evaluating the importance of getting a constellation approach.
Hi. Something really simple I do not get about meridional circulation. You showed it in 2 dimensions, but what happens in 3 dimensions? You're taking a whole bunch of material at the equator and trying to cram it into a little itty bitty space at the top.
Yes, exactly. And so that's why the question is, does that conveyor belt turn over and go down below? And the problem is, and this gets at what Devendra was talking as well, is that at the moment, we don't have the sensitivity to truly define what the flows are at the bottom of the convective zone. But we need to do that to understand if there is, for example, a reverse flow. So it goes up, so it's got to go down and under and come back out, if that is, in fact, what's happening. So observing the poles allows you to look at that subduction point of where the flows basically go down. But yeah, you've got to close that loop somehow.
A completely different question.
Yeah.
Solaris. Spacecraft last a long time these days. So if you have a mission and the orbit is from Jupiter around the sun and back again, it's going to spend most of its time out near Jupiter. But as long as it lasts a long time, you get the sampling over and over again to catch the solar cycle.
So you can have orbits, for example, with Jupiter and then using Venus to circularize your orbit, to allow you to basically not have to go so far every time. And in fact, Solaris can be designed to last for 11 years as an extended type thing. Pardon? What limits the life? Funding and resolve at NASA to a large extent, and ultimately other things, but that's the first order stuff. So yeah, you can. So Solaris could be the first of a constellation, and maintain that moving forward. So there's different science here, right? Because there's the immediate, just going high enough, long enough, we're going to answer some fundamental questions. That's the real impetus for Solaris. But then as we move on, we want to keep it going to get that solar cycle effect. And then we need the different views of a constellation to get that 4 pi view of the sun so that you really can build things up. Oh, okay. You probably want a microphone. So I can repeat the question. Essentially what he's saying is that there's not enough time, and I respectfully disagree with that because we did a lot of study to determine how long you needed to do to answer the questions we posed, which was about 3 months, which Solaris will get at both poles. But go ahead.
I also think it is very important to observe both north and south poles at the same time. Mm-hmm. But probably it's too long to wait for the orbit to come from north to south. But that's one thing. Another question is this open flux problem, and in situ measurement is always like 2 to 3 times more than the expected, right? But how important is the polar field measurement for understanding that? And John Linker, for example, pointed out the possibility that maybe polar field is not well captured. But what about two different methods of measuring magnetic field? One, remote sensing, another one is in situ. And the factor of 2 or 3 naturally happening in basically completely different measurement methods.
Yeah, so 2 things.
Yeah.
First of all, your first point, with a mission like Solaris, because it's 3 months at one pole, and it's just a few months later that it's the next pole. So it's not a long time. So you are seeing them at close to the same time of the solar cycle. Interestingly, of course, the North and the South Pole don't behave the same way during the solar cycle. So you might have the reversal of one pole and then the next. And so seeing them close together in time is quite important to pin that down. The second point was about, the open flux. Yeah, exactly. So if you could observe, now the magnetic field is pretty constant in the heliosphere from pole to equator. So it would be great to be directly above and observe the magnetic field in situ at the same time as the magnetic field at the poles, and that can be done. But in general, that factor of 2 or 3, that's something that just going above and looking down will rule out the possibility that Linker, Riley, those folks proposed, which was a top knot.
I don't want to kind of blame or criticize people, but the measuring magnetic field indirectly, like a Stokes polarimetry, maybe it can be completely wrong. I don't know. Also, another thing is that I did some extrapolation using Parker spiral and PFSS model, and it's the periods that we are connected to the polar region above 60 degrees is very, very small. So why does the polar field matter for the open field questions? If we are not connected to the
well, that's us, but that's not the rest of the heliosphere.
That's true, of
right.
course,
I mean, most of the heliosphere is connected to the polar magnetic field. Probably that's what needs to be
But the open
figured
field
out.
problem is a comparison between the expected field and the measurement at 1 AU at the ecliptic mostly, right?
So the ecliptic is really a very special place, right?
Exactly, yeah.
And so there is quite a lot of the closed field structure that is what Nariaki is getting at there, as well as the open field. So you get a lot of the transient structures coming through, and so it's more complicated. But really, it's the polar field that shapes the heliosphere. And there's all sorts of implications about that, including I mentioned the vulnerability of astronauts going from Earth to Mars. A lot of that has to do with galactic cosmic rays. And the sun's magnetic field is a wonderful deflector of galactic cosmic rays. But our understanding of that heliospheric magnetic field largely resides with our understanding of the polar fields, or lack of understanding. Over here, yeah.
This is a slightly crazy question, but the interferometers, the interferometry nerds, have some hope of getting to resolutions of, well, maybe 1% of a solar diameter at Alpha Centauri distances, 1/10 of a solar diameter at 10 parsecs. So is this interesting? And if so, what would be your favorite stars to get them to look at?
So you're asking if we could resolve spatially sort of magnetic structures on other stars?
If we had, if the imaging resolution were there and the polarization resolution
So
were
there's
there,
a-
which
I
is
ju-
out of question. Which is not
I
out of
was
question.
just looking at a paper, and I'm forgetting now the authors, but it was, and I think it was Hercules something, but they had an interesting rotational profile where it was actually slower at mid-latitudes than the equator and the pole. The relationship between solar and stellar is very much a two-way street. There's information that we get from the sun because we are seeing its astronomy with a zoom lens, right? That is really fundamental to understanding what's going on in the sun and by extrapolation to other stars. But we also learn from other stars because we can have simulations that say, okay, we just need to choose these things and so on, and we have our sun, but it's only one star. So yes, absolutely that's interesting because by looking at other stars' magnetic fields and flows, we refine and truly deepen our understanding of the processes operating on the sun.
Are there any other questions? I have one more programmatic. How close we are at this 4-pi configuration, and which is the timeline, and would it be an international effort to provide all these spacecraft?
That's a great question because on some level, the pole, we have observations on the Sun-Earth line, the SDO satellite, for example. We also have the Vigil mission, which is coming up, or Europe is doing, and is going to be at the L5 point, so observing one side. I believe Korea maybe has ideas for doing observations from the L4 point, which would be observing from this side. We're starting to build this constellation with the crucial missing piece, the poles. But ultimately, so I think we're quite close. But ultimately, we need to have a sustained effort because this is our space environment that we live in, and so we need to be able to get the full configuration in a comprehensive way.
So let me follow on that question, which is the 4-pi mission is ready to go right now. It's not really like we don't need any technology development for it or anything. And the study that we submitted to the decade that you are part of. It basically shows, yeah, it's feasible, and it's now that we can do it. The idea that you suggested that we have L4, L5, that's not going to work for simple reasons, because if you have, for example, the L5 is an operation mission that has different specs and all that. The L4, I'm not sure what's the timeline of the Korean mission. So ideally what you want to have a constellation with exactly the same instrumentation, all of them that are flying exactly on the same time and providing the measurements simultaneously. That way you don't have too much to cross-calibrate and everything, and you have the same type of observation all over the place. And Firefly is ready to go.
And I agree that, especially for the sustained global observations, that's going to be really important. I will argue that the discovery science of what we're going to find at the poles, we just need to send something as soon as possible, which is what Solaris is designed for. So.
Sarah, thanks for the interesting presentation. I have a question away from polar mission. If you look at the sun with high and high resolution, we see smaller and smaller structures. And there was idea about building blocks of solar magnetism that what Jan Stenfel suggested. And the KIST was built actually to discover these built-in blocks of solar magnetism. So I'm wondering what's your opinion and what the status of this?
Yeah, I mean, the thing of it is, it's like flux orbs. We saw talks in 390 in the last couple of days where you know, you see, there are flux ropes all the way down, right, to tiny scales. There are microfilaments that may erupt. There are large-scale structures in the solar wind. These kind of, as you say, building blocks require looking at different spatial resolutions. And DKIST is critical because it's designed to really get down to the very smallest spatial scale. So it's a very complementary approach to look in a smaller field of view, but with a very, very high resolution to understand fundamentally the nature of convection, for example, on small scale and how that relates to large scale is crucially important. So there's different kinds of discovery science. There are some that are driven by these sort of new wavelengths and high spatial resolution or temporal resolution. And then there's other science, mostly what I've talked about today, is driven by getting a global or 3D picture and synoptically constant observations as opposed to like one place than another place. So these are very complementary approaches. But the flatland thing, I think, really pushes us into a global view.
Okay, so if there are no other questions, let's thank again Sarah Gibson for this night.
1.2. Okay, I can hear myself. I can hear, yeah. Hey, hey, hey. 1, 2, yes. Hey, hey, hey. 1, 2, 3, 4. Hey, hey. Hey, hey, hey. 1, 2. I can hear. Hey, hey, hey. Hey. Now I can hear. Hey, hey, hey. Hey, hey, hey. 1, 2, 3, 4. Ooh, ooh. Hey, hey, hey. 1, 2. Hey, hey, hey. 1, 2, yes. It's in the review, yeah. Hey, hey. 2.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. So that. Hey, 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 hey. 2, 2, 1, 2, 3, 4. Sure. Because you want a bit of room against others. Can't pick up the. Switch the mic off. Because we turned the volume down. 2, 2,
You don't have headphones on there.
he, 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 he. He, 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 he.
Well, welcome everyone. Welcome to the Gruber Prize Ceremony and Lecture. I'm Deborah Elmgreen, President of the IAU. I'm delighted to celebrate the 2024 Gruber Cosmology Prize winner, Dr. Marcia Ricci, as well as the Gruber Postdoctoral Fellowship winners. The IAU has enjoyed collaborating with the Gruber Foundation since 2001, since we share the common goal of striving for a better world through science. With these awards today, we honor breakthrough science from a generational leader, as well as the promise of great advances from the next generation. For our ceremony, I'm pleased to have with us Executive Director Sarah Ria from the Gruber Foundation, as well as past Gruber Prize winner Richard Ellis, and IAU President-elect Willie Benz. So without further ado, congratulations to all our honorees, and I'll welcome Sarah to the stage. Thank you.
Good afternoon. Welcome to the presentation of the 25th Annual Gruber Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in our understanding of the universe. On behalf of all of us at the Foundation, we are pleased to be here in Cape Town to present the prize at the 32nd General Assembly of the International Astronomical Union. And thank you, Deborah Elmgreen, for your warm welcome. The Cosmology Prize is presented annually in conjunction with the International Astronomical Union, whose support and partnership has guided our efforts since the earliest days. It is my pleasure to introduce Willie Benz, President-elect of the IAU, who will say a few words about our fruitful collaboration.
Good afternoon, everyone. As was said by our president, the IAU is very pleased to have collaborated with the Gruber Foundation since the prize's inception. In this business, the IAU has an advisory role in the constitution of the Selection Advisory Board for the prize. As part of our collaboration, we are fortunate as well to receive an annual grant of $75,000 US to be awarded to postdoctoral fellows around the world so they may pursue education and research at a center of excellence in their field. Over the years, the fellowships have been awarded to young scientists from Algeria, Chile, Poland, Taiwan, India, Spain, Italy, Israel, Greece, Belgium, the Netherlands, the Russian Federation, Mexico, the UK, Colombia, Egypt, Ecuador, and the United States. So as you see, it is a global enterprise here. We usually receive between 30 to 50 outstanding applications, which, as usual, makes the selection process difficult. And this year, I must say, was no exception. Nevertheless, we managed, the selection committee, to come to a consensus and decided to award the fellowship money to 3 winners. And the winners are, but you know the name already, of course, Aldana Grishener, Jonathan Alexander Quirola Vasquez, and Honghui Liu. Congratulations to all 3 of you. Now let me just say a few words about these 3 outstanding researchers. Adriana will investigate the electromagnetic weak and gravitational signatures from the formation of the heaviest element in the universe and assess the contribution of massive stars and binary to our process enrichment across cosmic time. Jonathan Alexander will focus on unraveling a new type of transient population, the fast X-ray transient detected by Chandra, XMM Newton, and Swift XRT. To determine their nature and cosmic rates, he will identify their host galaxy and track their contemporaneous counterparts. Hong-Hui Liu will study accreting compact objects with X-ray observations. He will use the constraints given by polarimetric and spectroscopic measurements to derive the best coronal geometry. He plans to apply his model to archival data from simultaneous XIPE, New Star, Insight X, HXMT observation of X-ray binaries. Now, in addition to the fellowship, our winner will also receive a certificate from the IAU recognizing their achievement. And I have them here. So maybe we can, if we have the winners online, and here they are. Hello to the three of you. I'll show you your certificate. Here they are, the three of them. So that is the certificate. So while I have you on screen, I would like to really congratulate you again for being such outstanding representative of the new generation of astronomers taking over from us, slowly but surely. I wish you all the best in your scientific career, and I would like everybody to give them a round of applause. So that completes that part of the ceremony. Thank you.
Thank you, Dr. Benz, and congratulations to Aldana Greichner, Jonathan Alexander Quiroga Vasquez, and Hong-Hui Liu. It was fun to have them on screen. It would have been nice to have them in person. Moving on, the Gruber International Prize Program, established in 2000, recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. While we are here to honor the achievements of Marcia Ricci, let me mention that the 2024 Genetics Prize was presented at the Allied Genetics Conference on March 10th to Hugo Bellin. On October 6th, at the annual meeting of the Society for Neuroscience, the Neuroscience Prize will be presented to Corey Bargman and Jerry Rubin. Please note that nominations to the 2025 Gruber Prizes will be open until December 15th, and that we encourage nominations that reflect the breadth of the fields and the diversity of those working within them. Before we return to cosmology, I would like to acknowledge our co-founders, Peter and Patricia Gruber, whose combined vision and leadership established our International Prize Program, and whose care in doing so gave it the legs to stand on its own. Peter has passed, but Pat remains the heart of the program and is a lifetime member of the board of directors. Returning to cosmology, we are proud of our illustrious laureate roster, and we are so pleased to be adding to it today. The 2024 prize recipient was chosen by a distinguished selection advisory board. We deeply appreciate the knowledge, commitment, and enthusiasm that these advisors bring to the judging process. We could not do this without them. Let me now invite our 2023 prize laureate, Richard Ellis, to present the official citation to this year's prize and introduce the scientific accomplishments of our recipient.
Good afternoon. It's a privilege to read this citation. The Gruber Foundation is pleased to present the 2024 Cosmology Prize to Marcia Ricci for her pioneering work on astronomical instrumentation to reveal the breadth and details of the infrared universe. Her contributions to flagship space missions have opened new avenues for understanding the history and mechanisms of star and galaxy formation. She enabled the development and delivery of premier instruments providing groundbreaking sensitivity to near-infrared wavelengths to both the James Webb Space Telescope, particularly NIRCam as principal investigator, and the Hubble Space Telescope, NICMOS as deputy PI. Through these substantive contributions, along with her earlier work, Marcia Ricci has had a lasting impact on our understanding of the universe. Now, if I could add some personal remarks, just to embellish this very nice citation. I first met Marcia in 1978 at the Objects of High Redshift conference at UCLA. And for the younger people in the audience, the highest redshift object in 1978 was a cluster of galaxies at a redshift of 0.56. So that places the progress that we've been hearing about at this meeting into perspective. In the early 1980s, infrared arrays began to emerge from declassified military programs. And Marcia was a pioneer in exploiting and developing these early cameras. If it can be imagined, these early cameras were 30 by 30 pixels or so. And while they were small, they were considered a revolution at the time. And I remember myself using one of these cameras and realizing this was the birth of a revolution in infrared astronomy. That revolution has been championed by Marcia and her colleagues, particularly in space. These early cameras fueled the idea of the Spitzer Space Telescope, where she was also involved in the MIPS instrument as a co-I. But eventually, of course, the Hubble Space Telescope, largely up until that time an optical and UV telescope, had to have one of these new detectors. And of course, that led to NICMOS, where she was the deputy principal investigator. I was on the original panel, the Dressler panel, HST and beyond, which proposed the idea of a next generation space telescope. After that report, the James Webb Space Telescope was, of course, developed. But the concepts were very early in the 1990s. Marcia chaired the science working group at a critical stage in the development of James Webb. And as a reward for that, she was awarded the principal investigatorship of NIRCam, one of the premier instruments, of course, on James Webb. Now, progress in observational astronomy, in my view, is driven by two things. One, scientific vision and determination. And secondly, technical progress and expertise. And Marcia is that rare individual who excels at both. And innumerable astronomers, particularly many hundreds of them here, have benefited from her work as a result. So Marcia, I invite you to come up and receive the Gruber Prize for 2024.
I thank all of you for coming this afternoon, and I especially thank the Gruber Foundation for this wonderful award. When we were first starting to work on JWST, we thought that, gee, you know, it was supposed to launch in 2009, and it was going to be, you know, something amazing and all that. But instead, it took several decades, but we got there. And at the end of that, my real reward initially was just it worked. There's data from my postdocs. I don't have to worry about having wrecked their careers by making them work on this instrument for N years with no data. And so I'm just stunned that I got this award because I never thought of any reward beyond getting data that propelled us forward. So I was just amazed. So let me talk a bit about how we got to a launch in late 2021. It was Christmas morning, 5 a.m. in the US, and why I might have started along this path in the first place. So part of the story starts way before the idea of having the JWST mission. And there was a reason why the infrared spectrum was attractive for studying distant galaxies. And I will try to highlight some of that as I go along. Before I get too far into the talk, I want to thank numerous collaborators. The right-hand picture here, whoops, there we go. This is what we called the wooden JWST, a life-size model that Northrop Grumman made, and it visited a number of places. And this was the crowd of people working on the project already in 2005. And ultimately, over 10,000 people worked on this to make it happen. But I want to especially recognize this other collaborator. Please stand up, George, because many of the key things many of the key ideas that made NIRCam so successful, and also many of the steps along the way, were because of our collaboration. And talk about someone who supports you in your career. When your husband stays up late thinking about how to design your instrument, can't ask for anything more. Okay, and of course, one of the ironies for me of JWST is that you notice that George is the sort of the MIRI co-PI, and I originally joined the JWST project, the Ad Hoc Science Working Group, to promote the existence of MIRI, and ended up being the NIRCam person. So that's how it goes. All right. So when I first started working on high redshift galaxies, the goal for what we were trying to do was very different from what is going on with high redshift galaxies now. And with Hubble, he established that redshift is a distance indicator, and that then led on to many other things, including the development of what we called the Hubble diagram, which was a plot of apparent magnitude versus redshift in curious units, depending on how they did things in those days. And you will notice some curves superposed here with this strange parameter Q0 that we no longer use. It was called the deceleration parameter, and it was a stand-in for the total mass in the universe. And the idea was that by measuring how the brightness of a standard candle changed with distance, you could determine how much mass there was in the universe because of the mass changed the light path. And so people had established more or less that bright elliptical galaxies in clusters were standard candles, and so you could measure the brightness of those as a function of redshift, and you could map out whether or not the universe had enough matter to be a closed universe or a flat universe or would expand forever. So that was the initial game, and because it depended on measuring a brightness accurately as a function of distance, it was clear that because of the shape of the spectrum of an elliptical galaxy, the near-infrared would be a good place to pursue this initially, because the redshift would be moving into the infrared band, the visible portion of the spectrum, and we knew that very well. Whereas the visible portion that was getting measured, it was sampling the ultraviolet, which was not so well known. So the idea was it'd be more accurate to do this in the infrared. And let me just give a little presaging of where we would end up later. So if we look at the Hubble diagram for a cluster of stars, at a young age, that's a kind of age similar to what we're now measuring with JWST, and we look at the main sequence turnoff is quite hot, but there are already giant branch stars that have, or supergiant stars that have evolved from here. And if we compare where the tip of the main sequence is and where the giant branch is, with later times, you can see that it evolves down, and now we get down close to where we are today. But you notice that the giant branch color doesn't change much, but the luminosity changes by nearly a factor of 1,000. And so when we were playing this game of trying to map out the shape of the universe by assuming that galaxies were standard candles, we were fooling ourselves, because the luminosity of galaxies changes so quickly that once people realized this, there was no point in this Hubble diagram game. And we switched instead to thinking about how to measure evolution of galaxies. But let me give just a little overview of what it was like to measure galaxies at redshift of 1/2 to 1 in the late 1970s, early 1980s, before infrared arrays. So up here, you can see a picture from a paper by Rich Krohn, High Spin Rad, and others. And this object in the upper blue circle is a galaxy at redshift of 0.95. This was one of the record holders for a little while. And you can see it doesn't look like much. Down here is a Palomar Sky Survey plate, something that people have almost forgotten about now, but we used it for making finder charts. And so the idea was that if you were a near-infrared astronomer, you could measure this stuff if you did the following. You have a nice photometer, the detector's on the back, and this front eyepiece was what you could look through to get things lined up. And George had cleverly figured out a way so that, infrared astronomers always were given bright time because the OH airglow from the night sky is brighter than the full moon. So give us the full moon time because it doesn't bother us, but it does bother us in that you can't see anything to find, point at. So what George had devised was a photometer that included these, they look like just little handles, but they each ran a very precise screw that one full turn moved this eyepiece a millimeter. So if you measured the plate scale accurately, you could line up on a bright star, calculate the distance from that bright star to your object, turn the screws the right number of times, and that would and move the telescope to keep the guide star centered, and you could point at something faint. So you would initially point at this, start turning the screws, and the telescope would end up pointing at this galaxy shown here. That's how we made the following kind of plots. So we measured the near-infrared color, and this is the no evolution track, and you can see that some of the data were a little scruffy, but it was hard work. And then over here is a 2-micron or K-band Hubble diagram, and even this data set made it clear that the galaxies must be evolving and getting more luminous. And so by combining the fact that there's no color evolution and what we were seeing here. And then all of this definitely got propelled into a different direction because of the discovery of dark matter and so on. And that just rendered this whole point of trying to measure the shape of the universe from assuming standard candles just moot. It was a silly idea because obviously stars evolve and galaxies are made of stars, and so galaxies evolve. And this was before we even thought of all the complications of merging, et cetera, et cetera, et cetera. So Richard has already alluded to the history of JWST, and the HST and Beyond report came out here in 1996. That's what triggered NASA to actually start allocating real funds, not just sort of people studying things a little bit. And there had been various notions early on, but it wasn't until the early 90s that people could see that galaxies were likely to be compact enough and therefore not so spread out that they couldn't be measured. And by the time the Hubble Deep Field was imaged, it became clear that we weren't going to run out of a galaxy population. We were running out of the ability to measure them. And so we needed something else, which of course the arguments were well summarized in this report. And then JWST, but then called Northrop Grumman, not Northrop Grumman. There are people that said it was called Next Generation Space Telescope, had to be changed because the company was Northrop Grumman Space Technologies, so it sounded the same. And you can see along the top row some of the progress in detectors. So let me just make a minor comment, well, not so minor comment, about why it's important to go to space to do infrared work. I've already alluded to the fact that on the ground, the OH air glow is brighter than the full moon, which means that even in the near infrared, it's like trying to see a tiny faint thing against a very bright background. And if you go to the Miri wavelengths, it's even worse. So this guy is holding a match. But if you get rid of the background, it's so much easier to see. And that's the whole reason to go to space, is to get rid of that background. It also helps that there are some parts of the Earth's atmosphere that aren't very transparent at infrared wavelengths. So, precipitated by this HST and Beyond report, aerospace companies started thinking about what format there should be for something like JWST, and you can see some of the early concepts here, no one of which is exactly like what actually got launched. There was a lot of work to go, and there was a lot of technical development that was required to get at that time, 8-meter telescope down to a mass that an existing rocket could lift. One of the early D-scopes was to go from 8 meters to 6.5, and then the size stayed the same after that. So, and of course, along with this developing technology and things, another thing that was beginning to be understood, partly as a result of the Hubble Deep Field and work by Chuck Steidel and others with the idea of Lyman dropout galaxies, galaxies that where their ultraviolet radiation was all absorbed by the intergalactic medium. And so it became obvious that Hubble just wasn't going to do it. And I'll give you a little intro to that here. So here's the output of a galaxy at redshift of 3. And Hubble filters do a very nice job of outlining the output of that galaxy. And you can see that, JWST, of course, can do a lot on it as well. Now, if you move to Z of 7, you can see that this edge, very sharp edge, caused by absorption in the intergalactic medium, is wiping out the output of the galaxy. And at this point, at this redshift, HST still has some filters. But as we go to the last step in this little sequence, by Z of 10, you can see that the limit of HST is being reached. And some of the early detections, like GNZ11, that was the highest redshift object that HST ever detected, was basically detected by HST in only one filter. So you had to have some confidence that that one filter was showing you what you thought, and that wasn't some other extinction or a bright emission line or something conspiring to make you think it was distant. So it was by 1996 very clear that we needed a large cold infrared telescope in space if we wanted to go any further. And along in this same time frame, thank goodness, infrared detectors went right into a realm that would warrant being launched on a big, expensive mission. I mean, I remember when George and I got our first 32 by 32 array, a whole kilopixel. Can you imagine selling a digital camera with a kilopixel? No one would buy it. Well, anyway, we thought we'd died and gone to heaven. It was just fantastic. And as time went by, and partly as a result of the NICMOS project, we got larger and larger arrays, and Spitzer also helped propel the array development quite a bit. So by the time we were really serious about starting the AWST, we were getting into the kinds of arrays, and these are pictures of actual flight arrays, that warranted being launched into space and have provided the wonderful data that we have so far. And as George is fond of pointing out, we do better than, infrared detector arrays were doing better than Moore's Law for quite a while. So it's pretty clear that the idea for JWST was to penetrate as far back into here as we could get. And when I made this slide a while ago, I said, well, maybe you can get to Z of 15. We're at Z of 14.3 and counting. Stay tuned. I'm sure we'll find some more. And while JWST was being constructed, Spitzer was launched in 2003, and Spitzer provided a number of impetuses that really pushed the high redshift galaxy game further. And here, for example, are a couple of galaxies where the Balmer jump, which indicated relatively old stars, were being found at a redshift of 6 and 7. And again, no one had predicted that. But if you look at this plot of, here's several different galaxies, all from Z of 9 to 10, and you can see, the HST data, you can barely see these little dots. And unfortunately, Spitzer, they don't look very impressive because Spitzer's primary mirror, although it was very cold and could make very sensitive measurements, was smaller than one segment of JWST, which meant that the angular resolution was not very good. But this just whetted people's appetite. And another thing that was quite intriguing was that by making a lot of measurements with the IRAC instruments at 3.6 and 4.5 microns, and these two filters actually have very close analogs in NIRCam, you could see that there was for particular redshifts, there was a shift in this color that implied that something funny was happening, and that something funny was a strong H-alpha emission line in one of the filters. And we should have realized then that slitless spectroscopy on JWST was going to be a powerful tool because Mother Nature was providing us with extremely strong emission lines that would show up well in that kind of observation. And so now we get to where we're actually, we've gotten into the design of NIRCam, and you can see that it has two identical modules that point at adjacent pieces of the sky. And the reason that we designed it this way was that George and I reasoned that if we had the two identical modules, because NIRCam is the tool used to keep the 18 mirror segments co-aligned to act like a single smooth telescope mirror, if we had two identical, then in NASA's, this would be called fully redundant. And if something broke in one part of NIRCam, there was still the other part that could do this wavefront sensing. I have to say, as an aside, learning about all of the wavefront sensing, I really went past thin lens 1 in the optics regime. There was a lot to learn there, but NIRCam was equipped with the right parts to do that. And from the science point of view, having these two identical modules meant that we got to survey twice the area at once, which is very helpful for looking for high redshift galaxies and doing surveys. And you notice that there's a blue and red outline. The red outline is the footprint of a long wavelength array on the sky, and the blue are the 4 short waves. So not only do we have 2 patches of sky being measured, but we have 2 wavelengths being measured. And we equipped NIRCam with a nice suite of filters which have proven to be very effective at measuring photometric redshifts, which of course are aided and abetted by the fact that this problem for HST, that the intergalactic medium absorbs all the light below the Lyman limit, that makes a very good redshift indicator. We also were interested in combining imaging with spectroscopy, and NIRSpec has, for the first time, provided multi-object spectroscopy in space, and you can open and close its shutters. This was a real trauma to get this to launch because we discovered in one of the tests that vibration testing tended to break some of the shutters, and some of this had to be redone. Not fun late in the game. But they can be electrically closed and opened, so you could program what you were pointing at. But the one thing that was a little bit tricky is that for a ground-based multi-object spectrometer, you use a probe that you typically can move, or a plate that you drill holes specifically for your objects, and then you change the plate. Here, where the slits were was fixed on a rigid rectangular grid, and all you could do was open and close them, which meant that sometimes you had to make some compromises. And so first you had to measure some reference stars. This happens autonomously in space. It points, and where the reference stars are located is known. And what this does is JWST can rotate around a little bit. An exact precise angle is not quite good enough for pre-programmed opening of the slits. So you would have picked out the slits, and you would measure these reference stars, and then you could tweak up the rotation a little bit. And you will see that there are some, like this target here is right on the boundary between 2 shutters, and then there are other ones that are shown highlighted in green here that were good. And so when you plan an observation to get lots of high redshift spectra at once, you have to do quite a bit of work to figure out exactly which slits to open and things, and that's quite a bit of work. On the other hand, it's a whole lot better than having to measure one source at a time when it takes 100,000 seconds to get a good spectrum. And another thing that has complicated use of NIRSpec is just the laws of physics. So on the top here is 1.4 microns down to 4 microns. That's not even the full range of the instrument, but you can see that diffraction changes by just the ratio of the wavelengths. And so that makes calibrating the spectra some work. And one of the best things we found to do is to take the NIRCam image and project the slit pattern onto the image, and then you can figure out what fraction of the light is actually getting through the slit at each wavelength. And another thing that is tricky is that this is the number of spectra you might like to get, and this is the number of targets in the field of view. And if you don't have enough targets, you won't get to the optimum number of spectra possible, because there are too many that fall, on the cracks between the slits and things. So you need a high density of targets, but that's okay. Deep surveys for distant galaxies have lots of targets. And let me not forget MIRI. I will show some data. MIRI has proven to be more powerful at redshift 14 than any of us would have ever guessed. And in particular, more powerful than some of the NASA administrators at the time we were selecting instruments. And I'm so glad that I was persuasive enough, along with a few other people like Aveen Van Dieschroek, who was my co-collaborator in trying to get MIRI on this mission, that we succeeded. And it's, we haven't yet done some of the observations that I used to promote it, but it's very clear, since it's now the most requested instrument in proposals, that the mission would not be the same without it. So we've gotten to the point where we've actually built hardware. We did a test of the instruments cold and mounted them, attached them to the telescope at NASA Goddard Space Flight Summer in the summer of 2017. And then it was moved by aircraft to Houston Space Flight Center, and in Johnson Space Flight Center in Houston. We had the misfortune of being there when Hurricane Harvey hit. That was an exercise in and of itself, but the test was successful and kept going in spite of almost running out of liquid nitrogen. And then the last bit of construction happened at Northrop Grumman, went by boat through the Panama Canal, and ended up at the Ariane Space Launch Site in French Guiana. And this just shows going into the airplane, and that portable clean room that holds the telescope and instruments has only about 2 centimeters of clearance with this airplane. So the guy driving the truck was very skillful. And as it turns out, we had the same truck driver from here at Johnson loading it onto the airplane, all the way through loading it on the boats and stuff and taking it off the boat in French Guiana. So he was a very good driver. This shows the test chamber at Johnson Space Center, and you can see from the size of the people, this is huge. It was built to test the lunar rover, and the project had to do a lot of work to clean it up. It was not intended for precision optics to go inside. And you can see here's what it looked like. This purple stuff here is extra radiators used to get the temperature down to match what we thought we would have in space. And there was some test optics up here. Then when we got to Northrop Grumman, we got connected to the spacecraft and the sun shield. And here are the cables and things that go up to mate to the cables coming down from the instruments. And I'm very glad I was not the person that had to connect these. So we finally made it to late 2021. There is the launch on Ariane 5. And this unfolding sequence that I don't know how many of you ever saw the video of the unfolding, but when you would show that at a colloquium or whatever, there were a lot of astronomers that looked at me and said, "Are you nuts? Why are you spending so many years of your life? And that unfolding's never going to happen." And I would go to meetings in Washington, D.C., and there was a person who shall remain nameless, but he was a former CEO of Lockheed, and every time he saw me, he asked, "Do you really think that's going to work?" Well, the answer was yes, I did, and I'm glad I took the chance. But as you can see from the head of NASA Space Science at the time, you know, it was scary, and we were so relieved when we were relieved that the rocket worked right. We were relieved that everything unfolded right, because by the time we got down to here, fully unfolded, most of the things that could go wrong were behind us. So let me just talk a little bit about the launch. Here's the launch site in French Guiana. And also, I want to point out that this project is an international partnership, and there are 17 different countries that contributed to getting the equipment built. And it just shows what can be done when you have a diverse set of people working toward a unified goal. And if you, after, later in the meeting, you want to ask George about what it was like to get MIRI built as a collaboration between Jet Propulsion Laboratory and Royal Observatory Edinburgh, with all kinds of people from NASA, et cetera, in the middle, he can tell you that it was very important to have a completely unified front by the scientists. And he and Gillian Wright, who is his counterpart from the UK, were very good at making certain that they could clearly say what they were going to do, and that fended off some of the issues. And I also want to point out this picture that I got from NASA. You'll see that there are two pins that don't match. NASA forgot two pins. One pin is for the tracking station in Canberra, because JWST generates so much data that there are several downlinks a day, and there are 3 ground stations, one of which is in Australia. And then you notice there's a pin on Africa. And the European Space Agency has a tracking station at the little coastal town of Malindi in Kenya. And that tracking station, we launched from here, and we went off into space across here. And this tracking station was positioned perfectly to measure exactly what the trajectory imparted by the launch was, which meant that we could calculate how to do the first course corrections for getting to L2. And so this African tracking station played a role in making certain that JWST has this 20+ year lifetime because of the tracking that was available from there. So we got through space, we got through 6 months of commissioning, we got all the mirror segments aligned. This is when I finally did my, everything's okay moment. And this is a lovely diffraction limited, actually better than diffraction limited image. The combination of the mirror and NIRCam are diffraction limited down to 1 micron, which is quite a bit better than projected. And if you have sharp eyes, you may notice a few little blobs in the background. Those blobs are all galaxies, and this is when it hit me that this telescope that we had designed to detect galaxies, in fact, was detecting them all over the place. And there are some of the early release images of planetary nebulae that, I looked at first and I said, oh, it looks like, how's there a scratch in that picture? It was an edge-on galaxy. And so we say that galaxies like to photobomb pictures. And this just gives another graphic view of, here's a Hubble Deep Field image. You can see the spiral here and how much clearer it is with JWST. We had not expected to exceed the image quality of HST, but that's partly why many things are working better than we had thought, is the image quality is superb. Now, the other thing that, of course, matters is moving into the infrared. And so this is one of the early release fields, and it's blinking between HST and JWST. And the HST one has a slight greenish cast. And for those who are sitting close enough in the front, for example, there are objects like this one that only show up in the JWST image. The universe has shown us that there are many red galaxies, partly red because of redshift, partly red because of what groups of stars they have. Some are red because they've got a lot more dust than we would have guessed ahead of time. And so this increasing the spectral range that's available with this kind of spatial resolution is just, that's partly why we have to have whole sessions here dedicated to JWST results. And so that then brings me to the science that my team and I have done with this JWST Advanced Deep Extragalactic Survey, which is a collaboration between 3 instrument teams. And it's been fun getting everyone together on the same page, but it actually wasn't that hard. And the team has grown to be over 100 people now, most of whom are young postdocs and grad students. And we've divided up various parts of the science program, and different people are doing different things, but there's plenty of data to go around. And so the idea of the JADES program initially was to take deep images with NIRCam, use the technique of photometric redshifts to figure out what are likely to be distant galaxy candidates that we would want to take spectra of, and then you can see these little yellow slits here point NIRSpec at what we think are the likely distant galaxy candidates. Because unfortunately, as powerful as NIRSpec is, we can't, at the moment, at least with the amount of time we had as instrument teams, get spectra of everything. That doesn't work for us. We had to be choosy. And this is just an example of how well the photometric redshifts have worked. And yes, there are a few outliers here, but in the very highest redshift regime that you see over here, the IgM absorption causing the dropout shortward of the Lyman limit makes the redshifts pretty accurate and not so many dropouts. If you asked me to give you a sample of high precision kind of Z of 2 galaxies, that's a little bit harder. So we got our first sets of data in late September 2022. We analyzed them very quickly, and it turns out we had practiced, since there was a 2-year launch delay, we ended up being able to practice on synthetic data the whole process of analyzing, measuring a photometric redshift, and then transferring that information to the slit selection team. And so when we got the real data, we were ready to go quickly. And so you can see here how the short wavelengths are blotted out by the intergalactic medium, and there are in blue the data from NIRCam, and the red is a modeled spectrum fit to the points that's used to estimate the photometric redshift. So these were 4 that we picked out, and we were so happy that one of them was Z of 13, which we had not initially expected to find so quickly. And this just shows, here are the actual images. This happens to be the Z of 12.6 object. And you can see how there's nothing in the centers of the shortest wavelengths. And when you get to the longer wavelengths, you see it more easily. This just shows it graphically. And by luck, we were able to get those 4 in our first batch of spectroscopy. The original plan was that we'd get some imaging, and it would take a couple of months, we thought, to process it. And the end of the visibility period for good south meant that we probably would not be able to get spectra of objects selected from the first imaging. And so the first spectroscopic run was set up to target distant objects from Hubble Space Telescope data, because there were some interesting ones there. What happened was that NIRSpec has a little quirk that every once in a while it gets what's called an optical short. So one of the things that operates, one of the circuits operating a shutter starts glowing, and they have to go through a little procedure to clear it. And that happened just before our first spectroscopic run. And it was then going to be about 2 weeks before our data could be rescheduled. And so we needled Peter Jakobsen, who is our guru of slit positioning, and said, "What do you think, Peter? There are these four galaxies that fit in the pointings we already have. Can we sneak those coordinates in?" And he said, "Oh, no problem, because I have to go check everything, because 2 weeks from now, the position angle will be slightly different, blah, blah, blah. So we were going to have to change things a little bit anyway." So he got them in, and so we got these four objects, got the spectrum measured right away, relatively speaking, and we were ecstatic because our selection procedure had worked, and it had worked beautifully. And ironically, although in my mind, these dropouts were quite obvious, particularly in the 2D spectra down here, the referee said, "I won't believe this unless you get emission lines." Well, this is an object at Z of 9.4, a little bit lower than our 4 prime objects. And you notice over here, you can see 3 strong emission lines, 2 from 5007 and 1 from H beta. When you get to Z of 10, these fall off the end of the near spec sensitivity range. The detector no longer works out that far. And this is a very, quite a bright object, so you can see some other faint emission lines, which with the quality of data we had on our first high redshift ones, you could not see. So this was kind of, we didn't have this spectrum at the time that we had to answer the referee, but we danced around and he finally agreed to let us publish the paper. And this is just an improved version of that original highest redshift guy, because we got some more data later. And you can just see the outlines of the slits, and there it is in the slits. And so this redshift of 13.16 means that the light that we were detecting in this spectrum was emitted 327 mega years after the Big Bang. And that was just, we just could hardly believe that we had done this. And so at this point, we could say we've succeeded at the big goal. We said that we would take images, we'd get spectra, we'd find the most distant galaxies. But of course, whenever you have a record, it's meant to be broken, and I don't know exactly how long this record will last, but not forever. And so we have 2 more candidates that we found in some of our subsequent imaging and in a later round of spectroscopy. And one guy is at 14.32, and the other is at 13.9. And something that's very intriguing in the 13.9 is that it looks like we might even be seeing carbon in that galaxy at 13.9. And so I think we're, and I'll show some more evidence in a moment, we are challenging our ideas of how elements get formed in the very early universe. And one thing that's helped with this whole process, but it's also a puzzle that's challenging the theoreticians, is that many of these early detections, as shown on this age of the universe plot versus absolute magnitude, these galaxies are quite bright. And we're seeing this over and over and over, and there are various theories about, is star formation efficiency higher? There was an early debate about whether lambda CDM was broken, and we got rid of that fairly quickly, but nonetheless, there is something different about the star formation at these highest redshifts that we simply don't understand right now. And if you go and look at the poster session associated with the JWST symposium here, you find this coming up over and over. And I'll mention GNZ11, which Richard also mentioned in his introduction. And here is a nice spectrum. And when I first showed this to some of my colleagues at Steward in Arizona, they could not believe that this was at redshift 10.6, because you're seeing all kinds of metal lines that this was beyond our wildest dreams, let's just put it that way. But it helps that this object is indeed very luminous. And the existence of a nitrogen-4 emission line has prompted a discussion of how much light from this object is generated by an AGN or a black hole at its center, and that debate is ongoing. Now we turn to what MIRI has done for the high redshift universe, something that, again, our friends at NASA headquarters would not have predicted, because they said, we're going to run out of dust. You don't need to have a mid-infrared instrument if you're looking at the high redshift universe. What they forgot was that at the highest redshifts, MIRI gets to see our friendly old 5007 oxygen and H alpha. And this is being observed at redshift of 12.4. Amazing. I mean, this was a project that I would, even in my optimistic days on the old ad hoc science working group, I never would have proposed this as a way to justify MIRI. But here we are. It's showing how useful the mid-infrared is even at these high redshifts, and that's partly because the universe is cooperating. Things are brighter than we expected, and MIRI is going to be contributing much more in this arena, I'm very certain, because not only can it extend the range over which we can see our friendly rest frame optical emission lines, but we may be able to look for higher redshift Balmer breaks and so on to see just when the cool stars have started showing up. And we may also learn more about element enrichment. Not to be forgotten is that the spatial resolution of JWST is good enough that we actually can discern shapes, and there are parts of various teams busy working on understanding the morphologies of these high redshift objects. And we also have the ability to use medium band filters in NIRCam to isolate some emission lines. So this is the broadband image, and then here is a medium band image where you can see evidence of an outflow. And oops, yeah, no, this picture reproduced under this plot that I can't get rid of shows a lot of extended emission, most likely from H alpha around in here. And just what's going on with these extended emission line structures is, again, something we need to ferret out. Let me finish with a couple of special kinds of galaxies. This object, where it has very strong Balmer absorption lines, but yet is basically like an elliptical galaxy. We used to, in the old days, call these E+A galaxies. They're now called quiescent galaxies. And what's remarkable about this one, aside from the fact that it's at Z of 4.7, is that it has broad H alpha. And that's not something that's seen in these so-called quench galaxies in the local universe, or seen rarely. And not to be outdone, we have also a galaxy showing these strong signatures of an A-star population up at Z of 7.3. And again, we had not planned on finding galaxies like this at these redshifts. And last but not least is a paper that Joris Wittstock and Irene Chevalier led on some spectra of a galaxy at Z of 6.7. And you notice there's a little dip here. So this is the continuum of the galaxy. And you can see it magnified up here. This is the 2100 angstrom carbon absorption feature, dust absorption feature, seen at this redshift. And to make that kind of absorption feature requires a lot of carbon. And this plot shows this dashed line is, the limit at which you could presumably even see much carbon at these redshifts. And so, again, something different is happening with this star formation to get these kinds of abundances of heavier elements so early on. A little advertisement for those of you in the audience who want to go play with some data yourselves. We have released a lot of our data now and spectra as well, and you go to this site at Space Telescope Science Institute, and you can download mosaics, catalogs, spectra, and find things that we've missed, and I'm sure there are a lot of those. So let me just conclude by saying the best is really yet to come. We're only a couple of years into this mission, and many puzzles are being presented, and now with subsequent calls for proposals, people are going to be able to tune up their proposals and figure out what is causing these things that are happening at high redshift that we, at the moment, can't quite figure out. And I'll mention there are a couple of talks, plenary talks tomorrow. One from Richard here on the progress he's seen. And of course, ongoing all through today are talks in this IAU Symposium 391 at the West Ballroom down the hall. Thank you.
Marcia, thanks for sharing your remarkable behind-the-scenes story with us. How inspiring. We have time for some questions. Marcia, what I've admired about you for so many years is just all the remarkable development, just the forethought that went into these instruments. And I know you've shared with me a bit in the past, maybe the audience would like to hear, how did you start on this journey?
Oh, I started on this journey, I decided I wanted to be an infrared astronomer because I wanted to do something new and different. And when I was a grad student, infrared was, literally way out there. And when I was a grad student, I kept reading about these guys in Arizona that would kept opening up new wave bands and stuff. I said, that's for me. And so then George advertised for a postdoc. And thank heavens I got the job. And he had already been into measuring at that time, really nearby galaxies in the infrared, but again, it was hard work because you couldn't see them very well, and he'd worked out all these ways to pointing at something you couldn't see. And he got me really sucked into the galaxy game, and then when it came time for me to start thinking about, how do I want to make my own mark? And it was a time when there was a lot of ferment in finding distant galaxies, and we're trying to measure the shape of the universe, bad idea, but you could see that the trends for measuring evolution of galaxies were coming up, and it just seemed like the thing to do.
And we're all glad for that. Yes. Sarah. Wait, no, she's coming. She's running.
Running, but no tripping, please.
Thank you for this incredible inspiration from your talk and your work and your life. I'm just wondering, so of all of this amazing result, what's your favorite gem of your career and the results that you've seen?
If I look back over my whole career, there are two things. The first one happened quite a while ago when we took spectra of some stars at the center of our own Milky Way. And there was no doubt that we were seeing young stars there, which again kind of upended some theories because it was thought, you know, the center of the galaxy is old and dead and blah, blah, blah. No, it's formed stars within the last few 10 million years or so. And then once we've gotten into this JADES era, obviously one is stunned by redshift records and all that. But I have to say, when Joris distributed the startings of the paper with the Lyman alpha absorption, I just was stunned that something like that no one would ever, ever, ever have predicted we would see was there. And that was a galaxy we found in JADES, and Joris, you know, analyzed the spectrum, and Irene helped him figure out how much carbon there was and so on. And I couldn't believe, pardon me, that we were finding that kind of chemical signature now.
Thank you.
Yes, in the back.
Thank you. I have a question about the galaxy with the carbon absorption. And can we estimate it how much dust in this galaxy? It's possible?
Yeah, I think it is possible. And Joris Wittstock is here at this meeting, and he can explain how he and Irene did that more clearly than I can.
And one in the back. Yes, you have the mic.
Marcia, thanks for the wonderful talk. As an astronomy journalist, I've been following this field for a couple of decades. And ever since the early 21st century, astronomers have told me we are seeing galaxies so numerous, so massive, so early in the universe, our theories cannot explain them. And then the record was broken again. And now we are seeing galaxies at a redshift of 13.9 showing carbon absorption, apparently. I am wondering, what do you need to observe to really realize there's something wrong with our cherished ideas about early universe and galaxy formation? What else can we expect?
I don't know for sure what else we can expect, because if I knew what to expect, I might go off and try to figure it out. But we still have a lot of underanalyzed data, so there is that point. And this morning, if you were at the IAU symposium talk that Laura Pentorici gave, there's quite a bit more to learn about reionization and so on. But I think what we really are likely to need are more spectra, and in particular, the fact that we've now realized that MIRI can push out the limits to which we can see our sort of well-understood emission lines and things like the Balmer break. We'll be able to go to yet higher redshift, and we're going to get, we may eventually reach a wall that because of faintness we can't go any further. But I think there's a lot of stuff waiting to be done there to give us more clues about how the stellar population is coming together at these times, because we really have just had a few glimpses so far. I mean, the number of really, really high redshift spectra is still not large. And I think given the mission's going to last for 20 years, and we can therefore take some more really long spectroscopic exposures and take some with MIRI, we're going to figure, we will be pushing ourselves into a corner, I think, if we don't figure it out.
Marcia, the astronomical community owes you a debt of gratitude for your pioneering efforts, along with George, along with so many of you in the audience who are working on this. So congratulations again, many, many thanks, and thanks to the Gruber Foundation for recognizing this excellence. And with that, we conclude this ceremony. Thanks for being here. Thank you.
Release it.
Thank you. Yeah, it's not working for me either. Can you go back, please?
You just click the red button, you'll go back.
Yeah, it doesn't work. Back, 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 back.
Is that you or the text up there?
I don't know. Either way, it's not working. I know.
You want to go forward or back?
Either way.
Okay, let's go forward.
Okay, forward is good. Okay. Now let's go back. Oh, okay.
Let's just give it a, so you feel that click. It's for nervous people, but it's too soft, then it falls many slides.
Okay. Thank you. Oh, I gotta put my name on that. Yeah, okay. Okay, so yeah, it plays on click, you just need to click and be patient, which I'm not. That is blinky blinky. There's no sound in space. All right, so we got to take, yeah. I have a couple of changes to make too, so just, well, go ahead and make yours. Yeah, I have a couple of changes too. I need to make that I've noticed. Yeah, no, they're just like words or starts. Dos más. Yikes. Oh, you don't want to hear me anymore? I see you turned my mic off. Wow, they're just going for everything, aren't they? Chronograph, spectrograph. It's the final countdown. Yikes. Woo. Let's get physical, physical. Cute. Thank you very much.
Good evening. Can you sit down, please? Then let us start. Today, our preliminary title of the talk is Innovating the Periphery, Developing Radio Astronomy Technology and People in Africa with Radio Astronomy. And the speaker is Bernard van Roos. He is the South African astronomer and trained unionist and has been served in several positions in South Africa government from 1994 to 2000 related to the reconstruction and development program and to safety and security. And he did his first degree in Wits University in Johannesburg and PhD in Cavendish Laboratory in Cambridge on radio astronomy, and returned back in 1974 to Johannesburg and to teach physics at the Wits University and his research. And he became involved in very early stages of the organization of a new non-Russian independent trade union around Johannesburg in 1974, and left with us at the end of 1976 to work as a trade union organizer for the Metal and Allied Workers Union. And when the Metal and Allied Workers Union merged with other unions in the metal industry in 1987, and he was appointed as the National Secretary of the National Union of Metal Workers of the South Africa. And in 1994, he was appointed as the Deputy Director General of the Office of the President Mandela and head of the Office for the Reconstruction and Development Program, which was government's central program and of the government's development planning branch. At the end of 1996, and he moved to the Ministry of Safety and Security, where he chaired the Integrated Justice System Board and the Interdevelopmental Committee for Board of Control, and led to the drafting of the Act, New Firearms Control Acts. And he left the government 2000, and he started the South Africa's SK project as its director at the beginning of 2003 and retired at the end of 2015. The project includes our African bid for the SK, the design construction of the Meerkat and the observatory site at Losberg, and the Human Capital Development Program and the AVN. And he has a lot of experience in different government industries, in the trade unions, competitions, and now he is serving as the advisor in the Ministry of Trade, Industry, and Competition. And he will going to share a lot of experience in radio astronomy and as well as also the government duties. And I will invite Professor Bernard Landford for giving his speech.
Thank you very much for that introduction. My thanks to Deborah Elm-Green and the IAU for giving me an opportunity to speak about a project which is very close to my heart, and congratulations also to Kevin Govender and his team for putting together this whole amazing event. And then thanks to Mpati Ramatsoku, who's one of our great early career researchers. She's agreed to share this time with me. And thanks also to Wendy, who's kept me more or less sane over this entire period. So we really are in a golden age of astronomy, and I am quite jealous of the young people who are going to benefit from the data that's going to come from all our new telescopes. I felt quite out of date when I walked through the exhibitions earlier, because it really is quite spectacular, the momentum that's been created on astronomy around the world with the new telescopes, and in particular in Africa. And for those of you who haven't been to the Soraya stand, I really recommend that you go there, because it's an amazing stand, and it's just an amazing experience to see what has been happening there and with the SKA project. So working on the South African SKA project and the Meerkat telescope was one of the most exciting and fulfilling things I've done. I was privileged to work on what's really a one-of-a-kind project, but with an outstanding team of people who are totally committed to the project and to the good of the nation, and who taught me a huge amount about engineering and astronomy. So what little I know about engineering, I learned there. The African SKA bid and the design and construction of the Meerkat telescope show what can be done when there's a convincing narrative and when a nation agrees what must be done and throws its best people at the problem. And throughout, we enjoyed unstinting support from the Department of Science and Technology, which was initially led by Rob Adam, and then by Phil Njwacha, and by all our science ministers, especially Naledi Pandor and Derek Hanekom, and the president of the National Research Foundation, Khotso Mogeli. And then following my retirement at the end of 2015, Rob Adam and now Poncho Maraping have led Soraya, and they've done a great job implementing our wonderful site and the wonderful telescope. And many people played a role in the project, and I apologize, I can't thank them all. But one point I want to make before I start on my slides, and that is that I've heard a story that the South African SKA site was chosen for political reasons because countries felt guilty about colonialism. And that was, in fact, a rumor that went around before the site selection was done, but it's completely wrong. If anything, the politics were the other way around. People were saying, you can't possibly build this in Africa. The site was chosen on the basis that it was an excellent site and an excellent proposal for the site. So let us go on to the slides. I'm going to talk about some of our history in Africa's bid to host the Square Kilometre Array, how we developed and constructed the Meerkat radio telescope, and some of the innovative ways in which the Meerkat, its technology and its site were conceptualized and constructed. And I've got concerns about how much data is going to come from all these telescopes, and Mpati is also going to talk about that. We've also had very innovative programs on human resource development and how we can grow a vibrant astronomy community in Africa. So I'll talk about that. And then Mpati is going to talk about her experiences in this process. So, of course, you'll be aware that Africa is the cradle of humankind, and some of the oldest symbolic representation and technology comes from Africa. At the Iziko Museum in Cape Town, you can see this piece of inscribed ochre, which is 77,000 years old. So the first democratic government in South Africa was elected in 1994, and in 1996 it published a white paper on science and technology, and two of the priorities were that we should do fundamental research, not only applied research in South Africa, and that we should use our geographical advantages, two of which are astronomy and paleontology, because if we don't do these things, we'll be a second-class nation forever, and that was not a future that we were prepared to accept. And the SKA, being a global big science project, fitted beautifully into what we required. It does fundamental science and it does innovative technology. So I apologize that this is a rather text-heavy slide. I want to make the point that the SKA project in South Africa was a project of the government, but they had the good sense to leave us outside government structures. So we had a lot of flexibility and we were able to move quickly, and we could make a lot of our own decisions. Now, Khotso Mokgele, who was the president then of the National Research Foundation, had challenged the astronomy community a bit earlier after the construction of SALT had started by saying, what's the next big thing we should do? And the answer, amongst others, was we should become involved in the SKA. And Khotso says he was initially skeptical about astronomy, but when he was working on the SALT project, he realized that astronomy has an ability to appeal to and excite the public, which no other science has. So the NRF and the Department of Science and Technology formed a very small project team at the beginning of 2003 to bid for the SKA site. And as you know, the SKA is intended eventually to cover 3,000 kilometers with 2,000 dishes. So we involved 8 other African countries in our bid. And I think there was a convincing narrative as to why we should go for this telescope and how we should go for it. And the result was that as a mega project, everybody became very excited about it. The politicians trusted us, so we quickly got our own cabinet support. And then we got the support of the heads of state of the African Union. And we agreed that it was crucial to bid for this project because it would enhance our ability to get young people into STEM careers in Africa. And inside and outside South Africa, some people were very skeptical. They said, why do you want to spend money on astronomy when we've got problems with housing and food security and water security and so on? We also had a lot of Afro-pessimism, particularly from other countries, who said, you can't build the world's largest and most complex telescope in Africa, can you? And luckily, we ignored both of those pieces of advice. The World Economic Forum predicts that by 2035, more young people will be coming into the workforce than all the rest of the world put together. So that's a challenge and an opportunity. It's an opportunity because Africa will then have the youngest workforce, and the workforce in other countries will be aging. But it's a challenge because if you don't provide skills and jobs, then young people can be a source of great instability. And when I was watching the Euro soccer over the last month or so, what was very noticeable was that people from Africa or African descent were the stars in so many of the football teams. And I asked myself, why is that not true in our leading astronomy teams? Because I think it should be, and we have to change that. So we all know that science and technology is crucial to the development agenda. It has to be basic in all of our countries in Africa. So we started our SKA bid at the beginning of 2003, and our urban planner, Shireen Rawat, chose a number of options for sites. And the photo on the left is George Nicholson, who was then the director of the Hartbeespoort Radio Astronomy Observatory, with Shireen looking at some of the sites. And on the right, you can see the mobile cabins that we dragged around South Africa and to our neighboring states to measure radio frequency interference. And we were able to send in an expression of interest. There were 5 countries that bid. That was in May 2003. And eventually, after a lot more measurements and submissions, in 2006, the African bid, together with the Australian and New Zealand bid, was shortlisted for the SKA site. And there's a photo which must have been in 2011 of us finalizing our bid for the SKA. Adrian put together with Kim 45,000 pages, which was probably a bit of overkill for the people who had to read it. But they obviously did read it, and they seemed to like it. So in 2003, that was what our Karoo site looked like. That was the one we chose eventually. As you can see flying over it, it's very arid, it's very remote, and we thought the hills would provide useful protection against radio frequency interference. And on the right, you can see a picture of Professor Justin Jonas, who was our Associate Director, telling me where we're going to build the SKA, pointing at Losberg. And during the process of the bidding, the South African Parliament passed a law called the Astronomy Geographic Advantage Act, and that empowers the Minister of Science and Technology to control any activities in the whole of the Northern Cape Province which could interfere with astronomy. And as you can see, the Northern Cape is a pretty big part of South Africa's entire land area. And this is a map of population. You can see Johannesburg and Durban and Gqeberha and Cape Town, and this part is pretty empty. And there you can see the area around our site. There's the site, and there's Carnarvon, 80 kilometers away. And as you can see, there's not much there besides some sheep. So we had to establish a site on a very remote piece of land. Adrian with Eskom designed this low interference power line. We had to build 80 kilometers of road that's now tarred. We had to connect optical fiber to South Africa's backbone several hundred kilometers away. We had to reticulate the site. There's Tracy Cheetham, who was our infrastructure manager, is now the SKAO infrastructure manager for Southern Africa, switching on the power. And we also built infrastructure at the farm called Losberg, which is the core site for the SKA. So you can see here there's a buried bunker, which has got the power supplies, the backup power supplies. It's also got the racks, the computer racks, and the hydrogen mazes, and all the other things that we need. And there's a dish shed to build the dishes for the Meerkat telescope. So in 2012, an independent committee, which was chaired by Jim Moran from Harvard, recommended the Africa bid. The International SKA board then decided on a compromise with the SKA low in Australia and the SKA mid in Africa. The board also decided on a cost cap for the first phase of the SKA, which required a bit of descoping. So we now have the two sites, as you're aware, and you'll have seen the low antenna in the SKAO pavilion here, and you'll have seen the pictures of the first dish going up in the Karoo. But there's now 130,000 hectares of land there, which the NRF owns, and that's been handed over to SANParks, South African National Parks, to manage as a wilderness area, and all the rights of way and servitudes are in place, so we're really good to go. And of course, you can't do this without community involvement. And I must say, I'm very out of date. I was really blown away by what I saw. I recommend you go to the Soraya Pavilion. The amount of involvement of the local community and the crafts and other activities are quite amazing. So we had consultative committees, we had meetings with the community, we assisted small businesses to develop, but we focused on providing training opportunities for young people and to strengthen the schools, and that was our major focus. But as I say, I'm out of date, and I strongly recommend you go and have a look at the Soraya Pavilion, because it really is remarkable what's happened there. And there have been tremendous benefits. 23,000 full-time equivalent jobs have been created. There have been a large number of bursaries to school pupils, 259, and a whole range of scholarships for artisan training and so on. So in 2004, our South African Steering Committee decided to build a science demonstrator, which we called the Karoo Array Telescope. It was planned to have 20 dishes. And the idea was to develop our technology and science expertise, to give it a focus for the development of a radio astronomy community, and in case we didn't win the bid, It was to give us something to use even in the absence of the SKA. So we decided to build a general purpose telescope as an SKA precursor with the same technology, more or less. And then our National Treasury came up with extra funding, so we were able to go from 20 dishes to 80 dishes. We planned initially prime focus dishes, and the Afrikaans for more of the Karoo Array telescope is Meer, so we decided to call it the Meerkat. So that's how it became the Meerkat telescope. And eventually, as most of you will know, we changed from the 80 prime focus dishes to 64 offset Gregorian dishes. So we constructed two prototypes, the XDM, which is a glass fiber dish, the world's largest glass fiber dish at that time, which is at Hartbeespoort near Pretoria. And then we did a 7-dish prototype in the Karoo called Cat7, which worked so well it was actually used for science, not just engineering. And eventually 64 13.5 meter diameter dishes were built on an 8-kilometer maximum baseline. There are currently 3 cooled single pixel receiver systems, UHF, L-band and S-band, and we digitize the signal on the dish, which I'll talk about a bit later. It's got very good sensitivity and imaging and gets high survey speed from the good sensitivity. And we designed it also for commensal observing, so the digitized signal is broadcast to simultaneous users. And the amazing thing is it was completed on schedule and to budget. Not only that, but because of the excellent engineering work, we got twice as much sensitivity than we'd paid for no extra money. And now, of course, with the collaboration of the Max Planck Institute and INAF from Italy, the Meerkat extension is being built, 20 more dishes on a 17-kilometer baseline. So that's a picture of our dishes, which are good up to 25 gigahertz. And you can see the receiver systems there on the indexer with the digitizers and the other services. And those are the cryogenic receivers that were built for us that worked so well. So in doing the Meerkat project, we had a number of advantages. First of all, none of us had built a radio telescope before, and we didn't claim to know what we should build, unlike many other countries. We also didn't have to cater to the vested interest of a large astronomical community. There were only 5 radio astronomers, most of them on our project anyway. And we could hire excellent engineers who were very good radio and radar engineers and mechanical engineers, but they didn't know anything about astronomy. Another important advantage was that our mandate was to build the best possible telescope, not necessarily to develop new technology. Many of the other countries which were building precursors had to be able to persuade their governments that they would develop new technology in order to get money. And we luckily didn't have to do that because our politicians trusted us. So we made a number of important decisions as well. First of all, as I said earlier, it was a project of the government, but we were outside most of the bureaucratic structures, although the project has been more and more drawn in, and I won't say anything too much about that since the NRF is represented here at a very high level. But if they hadn't been, I would have said it's not necessarily a good thing to draw Soraya more and more into the bureaucratic structures. But I won't say that now. We were lucky also in that we had a top-level, highly accessible steering committee with the head of the Science and Technology Department, the president of the National Research Foundation. So initially we met every Monday morning at 7 o'clock in the morning, and we could get decisions very quickly. We built a telescope which was cutting edge, but not, as Justin Jonas used to call it, bleeding edge. So it was sort of mature technology, but not too mature. We also decided that we should have an engineering project, not one that was driven by scientists, because we knew that scientists want to continually expand the scope, and we wanted to actually build a telescope. So we made an engineering project. We decided to use system engineering, but with the flexibility for R&D because we were not building a nuclear submarine or a NASA spaceship. We also decided that we would make our own decisions, so we would hear what our colleagues overseas were saying, but we wouldn't be bound by that. And of course, underlying all of this was a commitment to using the project to develop skills and expertise. So system engineering, I think, was a basis for our success. Our Cat-7 prototype and the Meerkat did science when they were switched on, which I think surprised everybody. We used a flexible but rigorous system engineering model, and the way it works is you start with a user requirement specification, what your system has got to achieve, including the key science projects. And then from there you go down to the system spec. What do you have to build in order to achieve that user spec? And then you go down to the subsystems. What subsystems do you have to build to produce that system? And then you go to the component specification, and you do rapid prototyping. So you fail early and you correct early. It's much more expensive to do it later. So on our Cat-7, we tried Stirling coolers, and we realized they don't work. And then we tested focal plane arrays, and we decided they wouldn't give us the sensitivity we needed. And we tried multi-turret feeds, and we decided that those weren't right either. So those things we discarded very early on, and we went forward from there. Then once you've done that rapid prototyping and you've got everything in place, you verify that the components, the subsystems, and the whole system achieve their specs. And of course, you've got to do this with a very high attention to detail. And each subsystem team had a lot of autonomy. We said, this is what you have to do, get on and do it. And they had their own system engineers, and they worked with a great deal of commitment. And we benefited a lot from international advice and expertise, but we did our own thing where necessary. At that time, system engineering was not used universally. Also, there was a belief that to save money, because dishes are the most expensive part of the telescope, you can build floppy dishes and then correct your bad beam in software, and we didn't believe that, and we decided to build the best telescope we could, and our colleagues at the NRAO fully supported us, which gave us a warm feeling. We digitized the signal on the dish, which was also not common practice because the digitizers can generate self-generated RFI, but it was done so well that that was minimized. And we also decided that the flavor of the month at the time, which was wide field of view uncooled receivers, wouldn't work for us. So we decided to have the single pixel cooled, very sensitive receivers. And the cost optimization, we also realized that silver bullets don't work. So the way we did it was to optimize the system and each subsystem very thoroughly as it was designed and then in the construction stage. We brought some industry in-house, such as the company EMSS, and there was an exceptional focus and attention on detail. And in the photo you can see, you can see, okay, well you could if the laser was, there we are. That's Omar and Francois with one of our roach boards that was designed as part of the Casper collaboration and was led from Cape Town. We mitigated risk by hiring the best people. We had small and lean teams, a lot of autonomy and trust from our steering committee, good communications. We had excellent support from our international colleagues. Also, very importantly, we knew what could be outsourced and what couldn't, and how you can outsource for the best productivity. We had an excellent relationship with South African industry, but also with big international high-tech companies such as NVIDIA, Xilinx, Cisco, and Intel, and they were very open with their new hardware and also with their roadmaps, which was very important. And when we came to participating in the design of the square kilometre array itself, South African companies were reluctant to get into that, so our Treasury approved the setting up of a technology development fund where we could share the risk with South African companies, and many of them have now got SKA contracts. And quite early on, we realized that the volume of data that was going to be generated was huge. And so I asked our software teams to build what I call the serendipity machine, because I asked the question, when Jocelyn Bell was discovering pulsars, what she was doing was reading mile after mile of paper charts, and you could see there were wiggles on it. But when you've got a bucket of multi-dimensional data points, petabytes of them, you can't just look at this bucket and say, oh, that looks strange, I wonder what it is. So I asked them to look at the serendipity machine, which would go through all these buckets of data and say, oh, that looks odd, I wonder what it is. And Michelle Lochner's team at the University of the Western Cape and others have done excellent work. Michelle's program is called Astronomically. And as I understand it, this machine learning finds what they call latent spaces or manifolds. We need to think about how we relate those to physical quantities, but what you then do is you look for objects that either aren't on the manifold at all or are on the manifold but separate from where everything else is, and then you follow up those outliers. And my concern there is, are there enough graduate students in the entire universe to follow up all the outliers that are going to be generated by the SKA and the Vera Rubin Observatory and all the other huge telescopes that are coming online? And obviously we'll have to take artificial intelligence further, not only in following up, but even analyzing survey data and anomalies and linking multi-wavelength data. And I believe there's a lot of work going on in that area. I think it's crucial. And also one thing that worries me is that we're now getting huge archives of data, and there's a risk that they won't be looked at because everybody has to chase soft money. So you always want to go onto new surveys before you've really had a chance to go into the old surveys. So Oleg Smirnov and Ian Haywood and their team are processing the Meerkat archive, finding very interesting transients. Cyril Tuss, I believe, is doing that on LOFAR data. I really think it'll be tragic if we throw away our archive data because it's a vital resource for researchers who don't necessarily have the resources to get direct observing time on major instruments. And I was chatting to Min Nguyen about ASCAP. They also have a very nice archive which has data cubes and images, and we should be using that sort of thing more than we are, I think. So the Meerkat has performed very well, 330 papers published since July 2018. I was talking to Roger Blandford recently, the professor from Stanford, and he said the Meerkat's even better than you read in the press. So I thought that was quite a nice comment. And as you know, the square kilometer array, I beg your pardon, it should be the Meerkat Plus. I apologize for that. It's under construction. The first SKA 15-meter dish is now on site, and Meerkat will be absorbed into SKA Mid when there are enough dishes to justify the transfer, which Phil Diamond assures me is 2028. And I hope he's right, because I want to be able to apply for time on it. So there's the handover of the first Meerkat Plus dish in January this year. The main spin-off for me, although there have been other commercial spin-offs, the main spin-off for me of the Meerkat project has been in expertise. And a nice example is what happened when COVID hit us. Our Minister of Trade and Industry was deluged with offers from all around the world to supply him with ventilators. And he called us and we said, well, why don't we do this properly? And we got the Soraya engineers together with medical doctors and lawyers, and they very quickly agreed on a constant air pressure ventilator. And our Soraya team developed the design and conducted a tender process within a couple of weeks, and then South African industry produced 20,000 ventilators at a cost of 12,500 Rand each. And this was really a very successful project which depended on the expertise from Soraya. And one of the Soraya system engineers is actually working with Eskom, helping them improve their generator capacity, which is why you haven't had any load shedding recently. So thanks to Poncho for that. Poncho's made sure we don't get load shedding. So as I mentioned, one of the major motivators for this was to build STEM careers in Africa and the astronomy community. And there were a number of major programs that have contributed to that. Unfortunately, I can't talk about all of them. The SGA South Africa, which is now SARAO, Human Capital Development Program, which is a pipeline to take young people from school all the way through to early career research. SARAO has an intern program. The development in Africa with radio astronomy, the DARA program, and later the DARA Big Data program, which has been run by Bonita de Swart and people from the UK, Anna Scaife and Melvin Hoare in particular. The National Astronomy and Space Science Program, NASP, which Mpati will talk about. The AVN, African VLBI Network project, which we started, and which has now become the SARAO Africa program. The African Astronomical Society is growing rapidly and is catalyzing a lot of activity around the continent. And of course, the IAU Office of Astronomy for Development has been active, and the Pan-African School is also very active. So remember, in South Africa, we come from a history of apartheid. The photo there is a classroom in the 1960s. The apartheid government's theory was that black people, according to the Bible, are only hewers of wood and pourers of water, so the education should be appropriate to that. And that created a huge backlog for an entire generation. So in 2003, when we started the project, we had 5 radio astronomers in South Africa, and they were all white men. And all our engineers were white men except Clifford Gumedi, Anita Lurtz, and Tracy Cheetham. And I'm glad to say it's different now. So I won't talk about NASP because Mpati's going to talk about that, except to say that 17 of the NASP graduates are now teaching in their home countries. The SARAO HCD program, which we launched in 2005, was driven by Kim de Boer Anthony, who's here with us now, Daphne Lekwati, Bonita, and their team. And its clear objective was to bring young people in Africa into astronomy and engineering, give them world-class skills, create a vibrant radio astronomy community, and transform the research community. It was intended to be a long-term program to build capacity. And as I said, it was based on creating a pipeline, so you don't just take people and then drop them, you stay with them until they're in an early research career. We had to extend the program. Initially, it was just for graduate study. We realized there were not enough young black students coming through in engineering and astronomy, so we extended the program to bring people into undergraduate study as well. And we offered preferential access for students from the small towns around the site in the Karoo. But we found that very few kids were actually passing the school leaving exams in maths and science, so we couldn't give them university scholarships. So what we did was to bring in teachers to the Carnarvon High School, and then we gave scholarships to kids from the surrounding towns to come and live in Carnarvon and attend the high school there. And we also extended the program to train technicians and artisans because we discovered that people who are born in the area are more likely to want to work there, and people who are not from the area don't stay long. So we started training young people then, and on the left you'll see, you'll see our first undergraduate bursary holders. And Kirtley, I believe, last week gave a donation for 3 cups, 3 awards to be given in Carnarvon to the best performing school pupils. He's now working in Cape Town. We also started artisan training, and we trained contractors, small contractors, so that they could benefit from the various opportunities in road building and construction, in catering and accommodation and so on. And we created the SARAO research chairs to create strong groups at the universities. There were 5 research chairs, later a 6th. They're funded for 15 years with a review every 5 years. I think they've been extremely successful in creating these vibrant groups at the universities. And there's a summary of the Human Capital Program grants. You can see that there are nearly 2,000 of them. They've supported the research chairs and faculty positions, 34 grants there, and a number of artisans, 130 artisans, 84 national diplomas, and so on. Anyone who wants to ask questions, there's Kim sitting in the row. So the success factors, I think, are largely because our program had a lot of autonomy, a lot of independence to make decisions and not have to fit into a one-size-fits-all. So one important thing was that all our scholarships covered the full cost. Remember that kids from disadvantaged backgrounds don't have families who can subsidize them. So if you don't cover their costs, then they starve and they don't do well in their research. You also have to go out and be proactive. Students at schools who don't know what a career in astronomy or engineering means are not going to come forward. So you have to go and look for kids. You have to be proactive. You also have to be very hands-on because students from disadvantaged backgrounds don't have the social capital, the understanding of how to manipulate the world to your own benefit. So our team has been very hands-on with the students so that they feel that someone cares about them. And most of these students are the first in their families to go to university. So the families expect them, when they've got their first degree, that they should go out and work so that they can pay for their siblings to go through education. And we worked out a scheme with our research chairs to supplement the scholarships and fellowships so that students could continue to postgraduate study and not be dragged back into getting jobs immediately. I believe that this is being stopped. I think that will be a very bad idea. Very importantly, also, the students feel part of a team. So at the end of every year, the program has a week-long conference where everybody gets together. Every student has to present a paper. It's good for them. They feel part of a team. They meet international researchers, and they get used to presenting their work. So there's a summary of the grants from 2005 to 2024. You can see most of them are directed towards Black African people and women, and we're trying to rectify the small number of, relatively small number of women and of Black students. And one of the very notable things about this program is that the graduation rate is in the 90%. If you compare that with other national programs, you'll see that the graduation rates are in the 20% as compared to the 90%. And I think that's because of the hands-on and very caring way in which the program is run. Our Soraya chairs have been asked what their views are on the program, and one thing that stands out is that we don't have enough supervisors. We've got a very big cohort of early career researchers, but we need more supervisors. And if you're an international well-known and prominent researcher and you want to co-supervise, I think you should go and talk to Oleg and the others. I'm sure they'll be very happy to co-supervise with you. The internship program's also, I think, been very exciting. It was highly competitive and the best interns get jobs. And just, this is a very old photo from 2015. This guy's a lecturer at UWC. She's got a postdoc in Toronto. Oleg is still at Rhodes University, where he has been for a long time. She's got her own high-tech business going in Johannesburg, and he's the manager of our digital signal processing and receiver team, and other things. So I think that's been successful. This is a picture of the 2023 end of the year Human Capital Conference. You can see there are a lot of students there, and I think they enjoy it, and I think their supervisors enjoy it, and I think people like Rob Fender and others enjoy it, but Rob can speak for himself. Then one other thing that we did was the African VLBI network. We realized that our African partner countries weren't going to get dishes for some time. So Mike Gaylord, who was at heart at the time, suggested we look at redundant satellite dishes and convert them. So we started with a 32-meter dish at Kutunzi in Ghana, which turned out to be in very poor condition, had to be almost completely rebuilt. And the operation there at Kutunzi was used for training astronomers and operators and even artisans. And the operations there are now funded by Dual Use, so there's an American company which does satellite communication, which have put their dish on the site, and their rent pays the operations for Kutunzi. And of course, the African Millimeter Telescope is going to be built in Namibia. There's an SK dish being put in Botswana by the Max Planck Institute, and Meerkat will also be part of VLBI. So the African VLBI network, I think, is eventually going to come true, and I think it's going to be a spectacular network. So this is just some pictures of the Kutunzi dish, and there's Ghana, there's Justin helping people. This is a team in Ghana being trained by Anita Lurtz, and there's Anita with a team in Ghana at Kutunzi training people. And out of all of this came the DARA project, the development in Africa with radio astronomy, which has been a wonderful project. It's co-funded by the South African Department of Science and Innovation and the Newton Fund of the UK. They've recently got another £7 million to renew it. It does a basic training program in radio astronomy, and then it takes students to South Africa and the UK to do masters and PhD. They've had 326 students through the basic training, and 26 masters have graduated and 9 PhDs. And because that was so successful, we were able to start the DARA Big Data program in 2018, which goes wider than astronomy. It uses big data techniques for things like climate change, agriculture, and so on. There are 8 universities in Africa outside South Africa and 9 UK universities, and then 9 institutions in South Africa are all part of this. One of their projects at the moment is constructing small radio telescopes in the African countries. And very excitingly, the new money is going to be used to create 12 postdoc positions in African universities. And we'll have to make sure those people don't become isolated. There's got to be good cooperation across Africa and with the rest of the world. So there's one of the small telescopes which is being built. It was designed in New Zealand. First one was put in Mauritius, and another one will be installed in Kenya towards the end of August, I'm told. And there you can see a workshop on the installation, which was held at Rhodes University last year. And this is a picture of one of our data science workshops, also happened to be at Rhodes. And that's the 4th Africa Big Data School in Cape Town in 2023. Note that 18 of the 25 students were women. That was on International Women's Day. And you can see that this is actually getting a lot more women into these subjects than we'd hoped. So AFAS is the African Astronomical Society, now has 390 members. It's growing fast. And it's generated a lot of progress across Africa. And for the details, I suggest you read an excellent report which Charles Takalana has written. I'm sure Charles will be able to give it to you. There are 28 countries involved and approximately 70% men and 30% women, but there is an African network for women in astronomy. So a lot more telescopes are being built, optical telescopes and radio telescopes, HIRAX, the African Millimeter Telescope, the dish in Botswana, and so on. But our big challenge remains that we're producing a cohort of really excellent early career researchers. There's a notable gap between them and the few senior researchers. How do we facilitate the retention of these young people in astronomy and instrumentation? How do we allow them to move on to senior research positions? because we're going to continue to produce these excellent young astronomers. We want them to have a career. And I'm looking forward to a time when our astronomy teams internationally represent as many African stars as the football teams. Thank you, and I'll ask Mpati to take over now.
Hi, everybody. I am Patti Ramatsoku, as Bernie has mentioned. Firstly, I'd like to thank the organizers of this amazing conference led by Kevin Govender. Thank you to Bernie for inviting me to talk to you today. This is a super huge venue. So what I'm going to do is just give you a little bit of the background, my educational background, tell you how I got into astronomy, what I am doing now, and what are some of the challenges that are facing people in early careers, such as myself. So just to give you a little bit of a background, I was born in the Free State, which is represented by that red pin. I was born in the Eastern Free State, which is a very small town where there isn't a lot of light population. And at around the age of, 12 to 14, I would go outside, look at the stars, and just be fascinated by all the different colors I was seeing. Why were other stars twinkling and others didn't? Why were some red? I later learned that was a planet. And while others were moving fast, those would be satellites, and so on and so forth. And so from middle school, from intermediate school, I decided that what I would like to do is to be an astrophysicist. And so throughout my high school, all I ever did was to work very hard to make sure that I get to be this astrophysicist. And so when I finished high school, I packed my bags, traveled about 1,500 kilometers to the University of Cape Town. At the time, UCT was the only university that was offering BSc in astrophysics. There was also a young researcher there by the name of Tebe Midupe, because presentation matters, who was going all around the country doing outreach, just making people aware of astronomy. I got to meet amazing mentors and supervisors, one of whom is here today, René Krankotovach. All of my undergraduate at UCT was supported through the NASP and the Sarau HCD programs, which I will get into in a little bit. After my bachelor's, my master's, I moved to Groningen in the Netherlands at the Kaptein Institute, where I did a joint PhD with the University of Cape Town, doing amazing H1 science. After spending about 4 years in Groningen, I decided I would like to be somewhere a little bit sunny, and so it's very dark. And so when I was offered a postdoc in Sardinia, in Italy, I said yes, that is exactly where I would like to be. And so after my PhD, I moved to INAF in Cagliari, where I stayed for a couple of years. I am now back at Rhodes University, working with Oleg and the team at the Rhodes Center for Radio Astronomy. As I mentioned, I was part of NASP, which is this multi-institutional initiative that was designed specifically to train young astrophysics and space science program students in honors and masters. I have the QR code over there if you would like to know more about them. We had an amazing time during NASP. These are some of my colleagues whom I've seen today. That's in the middle, that's young Michelle. A lot of them have gone on to do amazing things in research. Some senior lecturers at universities. Hopelang, which is this person over here, is an assistant professor in Canada. Eli is a senior lecturer at the University of Namibia. You have Michelle, who's a senior lecturer at the University of Cape Town. So they've all gone on to do amazing things. It is through these programs, the NASP program, the Sarah Human Capital Development Program, that I was able to do the incredible science that I think I have been able to do. If you want to know more actually about the Sarah HCD, see a poster also by Mthutuzeli Samgaka, which is poster number 28552. The amazing things about this program was that it wasn't just about lectures. We would take these incredible trips. We were part of teams, and these people ended up being my colleagues. I've been lucky to be able to do amazing science, so these are some of my highlights of my career so far. I was able to study hidden structures behind the Milky Way, confirming some previous unconfirmed claims. I've been able to study jellyfish galaxies, which, if anybody knows me, I really love talking about jellyfish galaxies. We currently got some referee reports of the galaxy over here, which is thanks to Meerkat and the incredible innovation of Meerkat. It is now the best described and observed jellyfish with all gas phases. So, yay, Meerkat. I've gotten the chance to study filaments feeding huge galaxy clusters and understand the different mechanisms that affect those kinds of galaxies. Again, this is thanks to Meerkat. In fact, most of my research is just done with Meerkat data. But one of the most amazing things was that we were able to uncover unknowns. This is Galaxy ISO 137001, within which we discovered these incredible filaments that are connecting the radial lobes. We still are not quite sure what these are. We were seeing these for the very first time when we looked at this image. The funny thing about this galaxy was that we weren't actually really interested in it. When we were processing these data, we were planning to observe this data. Our project technical lead at the time, Spesihle Makatini, said, you know what, we should point our telescope at the center of the image because there's this bright source. It's going to be annoying. We need to be able to remove it because it's going to cause calibration errors. And because of that decision, we were able to discover this without even expecting it to be there. We still don't quite know what causes these things, probably magnetic fields, but who knows? It's new. So I've been able to do this incredible science thanks to Meerkat and these amazing initiatives, human capital initiatives, incredible technological innovations. And I'm excited. I'm excited about the future. I hope I get to stay in research for quite some time to continue doing this research. I was at a conference in Pisa recently, and somebody showed this slide. They were talking about wide field spectroscopy, etc. I looked at this slide and I thought, whoa, this is a lot of data. This is going to be a lot of data. These are many telescopes at many wavelengths. These don't even show what we already have now, particularly in the radio, which is where I work. It doesn't show Meerkat. We're not showing ASCAP. So I wondered, are we building enough capital to explore all of these data sets? Because these are going to create a lot of data. Our chief scientist, every time we try to get time on the telescopes, always says, but you already have so much data in the archives, you really need more. So this is going to continue being a problem if we aren't supporting enough people getting into positions in which they're able to explore these data sets fully. Yes, we will have AI, which will be great, and it will help a lot, the great work that Michelle is doing and others. But I think in the end, you'll still need a human being to really look at these data sets completely. And so I went and looked at the numbers. I spoke to Ross Skelton. I said, Ross, can I please have some slides because I need to know what the 20 years of human capital in astronomy look like and how many people have been supported and how many of those actually remained in astronomy. These are the two plots. The first one is just a cumulative distribution of the number of graduates from 2003 to 2024-ish, 2023. And the one at the bottom is from the Sarao HCD program. Between these two programs, there might be an overlap between here and then. Approximately 2,000 people have been trained, have gone through national diplomas, undergraduate, masters, PhDs, postdocs. A lot of those people, a majority of them, were from South Africa, with the rest from the rest of the continent. So I started to wonder, where exactly are all of these people? What happened to them? In this slide over here, this is again from the NASP at 20 workshop, which was recently held. This map shows you where people ended up being. They recently ran a survey, and about 250 people responded. And they found that about 60% of the people have actually remained in research. Majority of them are in South African universities and research facilities like Sarao, SAO, Sanzam, IDEA. The rest have gone off to do other things like engineering, business, some work in government. And I plotted the same, I made the same pie chart for the Sarao HCD, and these are the same numbers, so these numbers are a bit consistent. So about 60% of people have stayed. This is great. But those people aren't really in permanent positions wherever they are. They're in postdocs, or they're in these contract jobs that are not completely stable. And so in my last slide, I would just like to sort of highlight some of the things that are a bit of a challenge in research as an early career person. They say in South Africa it takes about 20 years to become a full professor. That is when your job is secure. However, our funding models need a bit of improvement because the director of NRF is here just looking at me. because studying for about 10 years is unfortunately a luxury that very few can afford in South Africa and perhaps in many parts of the world. I'm not even including the 10 years that one would be spending in careers where they have to keep moving and with secure jobs. And so around when I was around here, I started talking to some of my colleagues who are in early research and just asking them, how are you? How are you doing? Why are you still in astronomy? And what are some of the challenges that you're facing? And these were kind of the four main themes that I received. A lot of them say they get into post-PhD positions, but they don't have mentorship, so they don't know what they're doing when they start these amazing positions in early career. Some said they are tired of moving every 2 years. They don't have time to actually settle and establish their research niche. 2 years is not enough time to be able to do that, which is 2 to 3 years, which is the duration of a typical postdoc. And those who ended up going into the universities and teaching are so loaded with teaching duties that they never have time to actually do the research that they like to do or that they got into this to be able to do. Others say, well, there simply aren't enough permanent jobs. To be a professor takes a very, very long time, and there aren't enough positions at universities. So I think what we need are just more permanent research positions. But what I will say is this. the HCD programs works, and I'm very glad for the work that Kim and the team have done. When I was a student, I wasn't aware of how much happens in the background. Now I am, and I'm very grateful that I didn't have to be aware of that. These programs work, and it's really through the deliberate technological innovations that was combined with the HCD program, so the need to build human beings who would be using these incredible telescopes, that I was able to pursue my dream career in astronomy. My greatest hope is that these programs will continue getting funded, they will grow, and we could try to address some of these issues that early career researchers are facing, and that hopefully one day a young girl from the Eastern Free State will not have to travel 1,500 kilometers just to study astronomy. Thank you.
Thank you very much, really, Berner and Ramaso, briefing the genesis of radio astronomy in South Africa, and overall the highlights and the important talks in astronomy and here, also the career. Then, if you have questions, then 2 questions, 3 questions. Then if you have any question. Okay? Any? Okay.
My question to Bernie. So you said SKA, SK dishes, meerkat will be handed over to SKO after 2028. So what do you think is the most important thing to do before that?
Yenji, thank you for that question. I think the most important thing is to get as much as you can out of Meerkat and Meerkat extension. It's working so well, let's utilize it as far as we can. I think if we continue the current rate of production, it's going to do great things. Phil assures me 2028 there'll be enough SK mid dishes to absorb the Meerkat, so you've got at least 3 years. People who are experienced in construction would probably say add a year or 2 to that, but I believe everything Phil tells me, so 2028 is the date.
Any other question?
Yeah. Yeah, okay. So, I mean, I thought there was kind of an interesting tension between the 2 parts of your talk, which I recognize very much, and I wonder what the general thoughts about that are in South African society, because it happens in more societies, and that's that, of course, astronomy is a beautiful flag on the ship of STEM, and you use it to lure people into STEM and to develop, high-tech and scientific capital in the community, but not just for the benefit of astronomy. But then, of course, you get people into astronomy and it turns out to be a powerful drug. People, once they are in, would like to stay in astronomy. And then, so, you hope for more jobs in astronomy because you'd like to stay there. So there's a bit of an inherent tension there, right? You use astronomy to support a system that is bigger than astronomy alone. And once you get people in, those people actually like it so much that they would like to stay. So how do you deal with that inherent tension that we build into our system that way?
I think Mpati should also comment on this, but as you'll have seen from some of the data we showed, there is a significant drift of people out of astronomy into other jobs in the economy. But I think there's also a very important public outreach function, which is just to interest young people in science and engineering and to give them some idea of what is involved. So not all the kids who hear about astronomy from Carnarvon will go into astronomy, but they may well go into engineering or technical work, or study physics or study some other science, which they wouldn't have done if astronomy hadn't been that high-profile science. And Khotso Mokheli's comment, I think, is very important, that astronomy is the kind of science that the public is very interested in. It's more difficult to explain to them about fractures in solid-state physics or phonons or whatever. But Mpati may want to say something.
Yeah. So very shortly, I think the issue is just that by the time people get to early career researcher, they are at certain points of their lives. And the way things work currently are designed in such a way that they are not compatible with that stage of life, unfortunately. This is why we need to improve on them so that we could retain these people.
Okay, the last one question, the last one, if you have any. Okay.
So it's a question with a comment. So, you know, we sort of invested over the years in the HCD, right? Sort of to bring in more and more young people into the system. And as we've seen, most of them end up falling off, you know, towards the end because they cannot get, you know, full position. Is it not time that we sort of reverse the system for a while? You know, maybe just reduce on the investment of bringing people in and sort of put it into now retaining them for a while still investing slightly in bringing more people in. Then that way, you know, you also create the positions for those people that are now coming in up in the system. And then, you know, as the need would dictate, then you see how you would then put in your investment to sort of create a balance.
Thank you very much for...
It's a cool comment, actually.
Sorry, can I comment on that? First of all, I think you should all read Charles's report on the African Astronomical Society, because he covers there a lot of the very exciting things that are happening all over Africa. And I understand that, for instance, countries like Ethiopia and Rwanda want to participate in the SKA now and so on. So there's been a definite growth of interest around the continent, which the African Astronomical Society is helping to catalyze. But as to the question whether you can stop, I think there are other people who are better qualified than I am to answer that. But I think it's a bit of a problem if you say to people, we're not going to take any more youngsters into the system, and then they're going to say, okay, but you know, you told us that this was so exciting, and now you're saying you can't offer us anything. I think the negative vibes from that would not be good. You may want to talk about switching some money in the budget, but you know, if I were you, I would be going along to people in the NRF and saying, we know that your budget has been strained, and we know that the Treasury wants to take money away from you, but even so, don't you think that you need to enhance even further the programs which you've already initiated to take early career and mid-career scientists into more senior positions? But I do think we also have to look at the issue of mentorship. Parties made the point that there's not always enough mentorship. The SKA, the Soraya chairs, have made the point that they're very open to collaboration on co-supervision, because we just don't have enough senior supervisors here. So again, let me appeal to people in the audience that if they want to co-supervise, they should certainly come forward.
Okay, thank you very much. Let us really thank again the two speakers, and thank you very much. Thank you.